You're muted.
Hi everybody, and Миша, привет. Я вижу только
Добро.
вас. Тут. Мгм. Yeah.
Zhikan, I'm going to make you co-hosts. Just give me 1 second. Do I do this?
Hey, Michael.
Hey, good morning. So,
Good evening. Good
Uh,
everyone.
Жека? Мгм.
Hey, Misha.
okay, so we're now all co-hosts. Actually, I think I could just make you a host. What happens if I make you a host? Okay.
Hello.
Yeah. So, so Sylvain is not here yet, I guess. Uh,
Okay, he's here.
Yeah. Hi, Sylvain.
Hello, how are you?
Okay. Okay, thanks. Yeah. How
Yeah,
about you?
Hello, hello.
I am fine. I am in Zurich. Yeah.
Okay. Working with Artur?
Yes, yeah. So it's hot here these days. Yeah.
So,
So, Michael, maybe you want to make Sylvain the
Yes,
co-host?
I'm doing it right now.
I cannot do it from my side.
Yeah.
Mhm.
Okay. Okay.
wait.
It's fine.
Yeah.
Yes, it is perfect. Oh, yeah.
Hey,
Hello.
Professor Kang.
Hi, Silavan.
Hello.
How are you?
Good. Yeah. And you?
Fine. Kind of sure.
Yeah. It is a long-term visit to Zurich, Sylvain, so you
No,
will
but I was teaching in Zurich this semester, so
so
I was commuting 3 days a week. So it's my last week. I leave tomorrow. Yeah. So it was very nice.
so what did you teach?
I taught about surface dynamics, ergodic theory on surface dynamics, focusing on property that you can get with Yomdin theory. And so,
Hmm.
yeah, my work with Jérôme Buzy and Omri Sarig, mainly. Yeah. I am supposed to write notes sometimes. So yeah,
Okay. Is
it was very, very nice, very nice group here. Good students.
yeah, well, I did something like this like 4 years ago, maybe. Yeah,
Mhm. Yeah.
it was enjoyable. Yeah, it was probably the students were different. So,
Yeah.
yes.
Okay, shall we start?
I am ready when you want.
Okay, so maybe just a very quick word. I mean, welcome everybody to our semi-annual Advances in Dynamics, uh, I guess, mini conference. So we have 4 speakers today. Hopefully, because of the time difference, we have to stick to the schedule. So each talk will be 1 hour, including questions. And the talks have been recorded and hopefully recorded
Well, including questions, maybe
will be
a coffee
made
break,
available
maybe coffee break.
afterwards. So
Mishak, maybe coffee break should also be included in 1 hour.
coffee break should be included in 1 hour.
Yeah, should be
Yeah, so the speaker,
fast
the
coffee.
speakers should just try to finish a few minutes early to give us all a little breathing room if possible. Okay, so it's my great pleasure to welcome our first speaker, Sylvain Corvisier from CNRS, and he'll talk about the closing lemma for NO maps of R2.
Thank you so much, and thank you for the invitation. It's a huge pleasure for me. So I chose to talk about a work in progress with Enrique Pujals. So about surface dynamics, dissipative surface dynamics, and so including Henon maps on the plane. So it's the beginning of, so we had the previous works on Henon maps on the plane, but now it's the beginning of a project, and there are other developments that I won't discuss now, but that we have in mind. So to start with something general to explain, so one goal would be to say something about the dynamics of the largest possible class of systems, let's say on surface. So as a test, you can consider Henon family. So the Henon family on the plane is a polynomial family. So I wrote the equation. It's dissipative, so it contracts area. You have one parameter, which is a Jacobian, which is B. So there are many ways to study the dynamics. So there are strong works about Henon maps. we know that it's difficult, and among questions that have been addressed is the question of to find so to describe most of the orbits, so Lebesgue almost every point, and so to find physical measures of SRB measures, and so I think about work starting with Benedict Carlson, which are so it's a huge piece of work, and so I'm not talking about that. So for this work, you cannot describe these maps for all parameters. You have to select parameters. So I am not talking about that. I will talk about a different way to describe the dynamics, and with the goal to try to address very large collection of parameters. So what is the question we want to discuss? It's how to decompose the dynamics. So what are natural pieces, elementary pieces to decompose the dynamics, and then to discuss how these pieces are organized together. So it's more topological, even if it may look simpler. There are difficulties. We know that we cannot avoid phenomena that comes from a Newhouse, which is Newhouse phenomenon. So, which say that for many parameters in the sense of Baire category, you have an infinite number of things. But if you decompose the system with trapping region, you will get, in fact, uncountably many pieces. So it seems very difficult to say something about the system. So let's see what we can say anyhow. So before that, I will motivate our result by presenting all the results. So the first one is in dimension one. So what can you say in dimension one in this perspective? So let me state a result. I didn't find this result in the literature stated like that, but I am sure it's already known. I found a paper by Bloch, for instance, who contains similar results. So it said that consider a map which is just continuous on the interval, and then there exists a family of pieces. So pieces in the sense they are transitive sets. And so they cover all the dynamics, they capture all the dynamics because any orbit, any forward orbit accumulate on one of the species. Then the species are elementary in the sense that the intersection is small, so it's a finite set. And then if you want to describe a bit what you have inside the pieces, so for some of them, it may be just a sink, for instance, so it could be a periodic orbit, or it could be larger. It contains, in this case, a dense set of periodic points. And you have also sets which have no periodic points, but they have a nice combinatorial description. So we call them odometers because you can approximate them by a cyclic permutation. So you have a collection of disjoint intervals that are cyclically exchanged, and that defines a small neighborhood of your set, and the period is arbitrarily large. Okay. So this is a result that is very much in the spirit of what we would like to have in yes.
Technical question. Is the talk being recorded? Mish, have you recorded the talk?
So the whole meeting is being recorded.
Okay.
And it should be in the cloud, so we should be able to
thanks. Sorry
share the links.
Yeah. Okay.
No problem.
Yeah.
So what do we have on surface in higher dimensions? So here is a more recent result we proved with Enrique Pujals and Charles Tresser. So this time it's for Hénon maps. the condition is that the Jacobian is less than 1/4 for a reason that will appear later. And we discuss the case where the entropy vanishes. Okay, and then we find again a collection of transitive sets which capture all the forward orbits. This time the sets do not intersect, they are disjoint. And each set is either a single periodic orbit or an odometer. So like before, you can define a neighborhood by the iterates of periodic topological disk. Okay. In this case, you can separate, in general, the set by renormalization domains. And so we prove that result, assuming the entropy is 0, but we developed tool doing that. And so then we thought that, okay, with this tool, is it possible to say something also when the entropy is positive? And so this is what I want to explain now. Before that, let me give other results on surface that are, so a very classical one is a case of hyperbolic systems.
But in the previous result, you also showed that eventually the periods are doublings.
Yes, so I say another thing we want is to describe how these pieces are organized together and to add more information about the periods, for instance. And so in particular here, yes, if you look to an odometer, we know that, so we have this nested sequence of periodic neighborhoods, so a sequence of periods. And we know that eventually the period is doubling. So from one set to the next one, the period is just the multiple of 2. Yeah. So we know more than this statement. Okay, so now in the hyperbolic case, so hyperbolic case in some sense, axiome, we know that in this case, you still have a finite, some transitive set, but this collection becomes finite. The sets are disjoint, and then we have a very nice description on the sets. So the sets are maybe just a periodic orbit, a sink, a source, or saddle, but maybe larger, like, so I pictured the case of a horseshoe or a Plikin attractor. And you may describe, so there's a more complicated set. So classically, you say it's a basic set, but let me say it's a homoclinic class, because homoclinic class is a notion that will appear in the more general setting. So let me say what is a homoclinic class. So how to find a piece, for instance, for hyperbolic diffeomorphism, once you have a periodic point. What is a piece associated to a periodic point? Okay, so consider a periodic orbit which is saddle hyperbolic and saddle type. So then you have at any point of the orbit a stable curve and an unstable curve, and you consider all the transverse intersection point between all the stable and unstable curves through all the iterates of the orbit. You find a set which is invariant. You take the closure, and it's a compact invariant set, which has nice properties. So it's always a transitive set. Okay. It's somewhat generalized, the basic set in the uniformly hyperbolic setting, because it contains very large, it's an increasing union of large uniformly hyperbolic sets. But at the limit, you capture non-uniform behavior. Another way to define homoclinic classes when you have a periodic orbit is to consider other hyperbolic periodic orbits that are homoclinically related, so such that you have orbits that connect one to the other, so transverse intersection point between the stable and unstable manifold of the two orbits. And again, you take the closure of this family of all periodic orbits homoclinically related, and you find the same object as what I defined first. Okay. So these are good sets, good candidate to be pieces of the dynamics. So you may try to play with that definition, and instead to consider transverse intersection points, since we are on the surface, you have curves, and you may look to non-transverse intersection point, but just crossing intersection. Sometimes you may have curves that are tangent, but still cross topologically. And so it's possible to play in the same way with a more topological viewpoint. But in fact, it turns out that when your system is infinity, there is a SARD-like result, which tells you that the set you will get in this way is the same as before. So for that reason, sometimes it's easier to assume your infinity in order not to distinguish if the intersections are transverse or not. It's not the question I will discuss. So all the arguments I will do are very topological. Even if I consider smooth system, I will play with topology. So the curves that appear when I have stable or when I have periodic orbits from the stable and unstable manifold, then I will consider them as topological objects. Okay, and then on the homoclinic classes, not only they are transitive, but there are many good information you have which generalize the uniformly hyperbolic case. So I summarize some of them that we proved. So first thing was proved by Katok. So the fact that these homoclinic classes cover all the measures with positive entropy, all the measures that are non-uniformly hyperbolic. Then the classes are maybe not disjoint, but their intersection have zero entropies. Their intersection cannot support measures that are hyperbolic and not just a periodic orbit. And their number is not finite in general, but if you consider with respect to the entropy, again, the number of classes whose entropy is larger than any fixed number, it's finite. Okay. And then you may do some ergodic theory on the classes. So for instance, if you consider measures maximizing the entropy, for each class you have one measure which maximizes entropy. And this measure has a nice property. It is a Bernoulli measure. Up to the period of the class, you have quantitative mixing, so you have exponential mixing. And then you have limit theorem, for instance, central limit theorem. So many things that I won't discuss more, just to say that these are nice sets to consider. Okay, so now what do we have for general Hénon maps? So if you have, let's discuss the measures. So if you have a measure which is hyperbolic, it's captured by the homoclinic classes, as I said, by Katok's theorem. And what about measures which are not hyperbolic? So I will talk about the dissipative regime. So measures will always contract at least in one direction, and possibly have a direction where you are neutral. You do not contract. Maybe you don't expand. And so this is what you would like to discuss. So there is sorry, I put an assumption. What I'm saying includes Hénon maps with Jacobian less than 1,4, all Hénon map with Jacobian less than 1,4, and then it will cover a larger class that I will define just after, which are merely dissipative diffeomorphism. So, but for the moment, let's think you have a Hénon map with Jacobian less than 1/4. And then with no further assumption, the result tells you that if you consider any ergodic measure, then you have a trichotomy. So it could be supported on a periodic orbit, or it's aperiodic, and then you may be supported on a subset of a homoclinic class, an infinite subset, or you may be an odometer, so something like what I described before. So let me give an example. So here you have a dynamics on the disk or on the plane. Assume you have a fixed point, which is a saddle in the middle. So it has a stable manifold which splits the plane in two parts, and then the two regions on the left and on the right are exchanged by the dynamics. So you consider the return map after two iterates. So for instance, to the left, you have a new fixed point, which is a new saddle with a stable manifold which decompose this half disk into two subregions, and it's the same for its iterate. So you have four regions that are exchanged, and the return map at period 4 again decompose with a new periodic point of period 8, and you continue in this way. So you have a sequence of saddles whose period are 2 to the n, and they accumulate on a set. So you have a decomposition of the dynamics with trapping region, and at the limit you find a counter set whose dynamics is combinatorially very well understood and called an odometer. So this is something that exists, and so this is one case of the trichotomy. Okay, so we say that all measures have to fall in one of these categories. Okay. So I said it's not only true for Hénon maps with Jacobian less than 1/4, it's true for a larger class of systems that are that we call mildly dissipative. So let me introduce that class of systems. So we focus on diffeomorphism of the plane that are dissipative. So the Jacobian is less than 1 everywhere. So for any measure, ergodic measure, which is not just supported on a sink, then we know it has one direction, one Lyapunov exponent which is negative, and another direction where the Lyapunov exponent is not negative. So maybe 0, maybe positive. And so at any point you have a stable curve which corresponds to the negative Lyapunov exponent. And so you look to this curve, how it embeds in the plane. And so you require that for any measures, not a sink, this curve separate the plane. So you have two branches which have to escape to infinity. When you put all together all the stable curve you find in this way, you get a kind of lamination of the plane, which is invariant.
Silva,
Yes.
it seems like
Hello.
Salim has a question. Hi.
Yes.
And just
Hello, Selim. Yeah.
Hi. Thank you very much. Thank you, Amy. I had a question about the general meaning of your theorem. Should it be understood in the sense that away from homoclinic classes, the dynamics is simple, or?
Yes, but this is contained in, if you were at the beginning of the talk, so if you have no homoclinic class, you know the entropy is 0. And
Yes.
when the entropy is 0, we have a much more precise description. It's a theorem with Enrique and Charles Tresser
Yes.
that I stated. And so the dynamics is simple in the case that, in the sense that it's described by periodic points and the accumulation set that are only odometers.
Okay, so that's the part that is surprising. You're excluding a lot of things by being able to say this. Is that how I should understand it.
Yeah, you can. But so it said that you don't have ergodic measure that sits on sets that are more exotic than odometers or homoclinic classes.
Okay. I see. That was my question. Thank you.
Yeah.
That's right.
Okay, so you may think that so this class mild dissipation is strange, is a strong assumption, and but in fact, it turns out that it's satisfied by Henon maps with a Jacobian less than 1/4 because of so the 1/4 comes from a result in due to Wiemann in complex analysis. So when you parameterize stable manifold, you look to these maps are in situ, you parameterize stable manifold, and then appears some entire map, and you describe how this entire map escape to infinity. And so it has played already a role in dynamics, in complex dynamics, for instance. So Michal Ljubic and, for instance, Romain Dujardin have considered this notion before us. They were more focusing on periodic point, and here we propose to look at it for all measures. Okay, so why is it interesting, this notion? Is that because when you have a lamination on a surface, transverse to the lamination, you have a structure with a one-dimensional structure. You have a tree, and so if a dynamics preserves a lamination on the surface, it means it preserves the transverse object, the tree, and so you have a one-dimensional dynamics hidden somewhere. Okay, and so this system can be thought as intermediate between 1D dynamics and system on surface. So there are arguments in dimension 1 that you may expect to push to dimension 2 using this class of system. And so that's what we do. Okay, so we introduced that notion, we studied that notion before, and we proved this result with Enrique that you can call closing lemma. So it said that any measure, so the support of any measure is accumulated by periodic orbits. So okay, so the argument is quite short. I will. So again, we were inspired by what happens on dimension 1, so on the interval. So let me give the proof. So before I gave just a motivation, we use that tool among others, but as a key tool to study diffeomorphism with vanishing entropy. When the entropy vanish, you want to see how odometers appear, for instance. So a first thing we proved is to show that all periodic points with a large period are covered by a finite collection of disk, attracting disk after some period. Okay, like on the picture. So if you know that, then if you apply the closing lemma, you know that any measure which is not supported on a periodic orbit has to be in the limit of periodic points with very large large period. And so any measure with which is not periodic has to be supported only on this disk, attracting disk that I have pictured here. Okay. But now each of these disks is periodic, and so at the period you get a new system, an induced system on a disk, which itself is mild dissipative. The mild dissipation is preserved under iteration. And so you apply again the result, and your aperiodic measure has to be supported on a smaller collection of subdisk. And you can continue. inductively and find a nested sequence of disk of higher and higher period that approximate your measure. And so your measure has to be in the intersection and has to be an odometer. So this is something we used.
And how do you construct the strapping disk? Just the idea.
No, but to construct the disk, it's a long way. It's
Just the idea.
it's not that easy. So it's very topological. Again, we use a lot the so periodic points. We know that we have for each period you will have you cannot only have things because of index properties. So you will have points with stable curve and also unstable curves. And then we want to play. We see how the unstable curves of periodic points are linked together, and we see that all periodic points of period up to some period are linked together by their stable, by their unstable manifold. And from that, we try to we can check that there are some weak recurrence. So the not some weak, no, the entropy is zero, but there are you try to find regions that are almost enclosed by curves inside the unstable manifold. And playing with that, you able finally to build trapping regions. It's a long story, but I won't use that. Okay, I will give an idea or the proof, in fact, in dimension 1 of this closing lemma. So you have a measure, take a typical point for the measure, x here. Assume the point is not periodic because otherwise it's already approximated by periodic point, it's the point itself. So you have return close. So let's consider a return. Here it's y, the point y. Assume it, consider one which is very close. And if you find a periodic point between x and y, you have a periodic point very close to x. So you're happy. So this is a goal. Okay, so you have x, you have y for an iterate of x. And then you fix this iterate, fn, and you continue to iterate. And you know that y, so x and y eventually will come back closer to x because almost every point is recurrent. And even for a typical point for a measure, your accumulated, so the recurrence is both from the right and the left. So you know that you will have a forward iterate for the map Fn, which is here on the picture on the left of x. So you look to the first iterate. So it's, I denoted it by y prime here. So it's it happens for the iterate L. So you have that y prime is the iterate FLN of y. Okay. So if you look to the point FLN of x, it's the previous iterate by the map Fn, and so it is a point which is not to the left of x, it's to the right. Okay, and you have an iterate x prime. So it means that for this fixed map FLN, you map x to the right of x and y to the left of x. So you have an interval xy whose image by this special iterate has exchanged the order on the endpoints, and the interval xy intersects its image by FLN. And so just that guarantees that you have a point fixed by the map FLN, which belongs to the intersection of the interval and its image. And so this point has to be between x and y. So it's
typical Sharkovsky argument.
Yeah, it's Sharkovsky says more, but yeah. Okay, so you have many periodic points. But in fact, you can say more. So let me add a remark. among this periodic point that you built, you may find one which has an unstable neighborhood. So let's say an unstable manifold, which covers the point X. So why do you know that? So here is the reason. So you found a first periodic point for some iterate. Now you can always take a larger iterate of this map so that the point is still fixed, but the point X itself is recurrent. So eventually, for large iterate, will come to the left of X, not like no, yeah, to the left. It's not the right picture here. Okay, so X comes to the left of itself, and P is fixed. Okay, and so maybe you have other fixed points for the same map now that are closer to X. So you take the fixed point which is the closest to X. And so let's assume this is P. So now what you find is you have X, a point P fixed by some map. This map sends X to the left of itself, and you have no other fixed point between X and P. Okay? So just because of that, you know that the topological behavior near P has to be repelling, and when you look to the repulsive basin, it has to contain X. Okay? So this property motivates a generalization in dimension 2, which is this result that we proved with Enrique. So consider, so now in the class of mildly dissipative diffeomorphism of the plane, consider any measure, assume it's non-atomic because otherwise it's already well described by periodic point, of course. And then not only typical points are limit of periodic points, Qn, but you may require for this periodic point Qn to be, so to have a stable arc that is close to the stable arc of X, close in the sense of Hausdorff topology, and which have, so I don't know if Qn is uniformly hyperbolic, but at least it has an unstable arc, at least on one side, and this unstable arc crosses topologically the local stable manifold of X, okay, like on the picture. So if you think about Katoch's theorem, when the measure is hyperbolic, it tells you that the point X has a stable manifold, but also an unstable manifold, and then you find there is also a non-uniform closing lemma, which tells you can find periodic points Qn close to X, but this time the unstable manifold of Qn crosses the stable manifold of X, and the converse is true. X, in this case, has an unstable manifold, and it will cross the stable manifold of Qn. So we don't have this second part, we just have half, okay? But we don't assume the measure to be non-uniformly hyperbolic. Okay? So what I want to do is to explain how we use this property to find this classification on measures, so this trichotomy. Okay? So I take a measure, ergodic measure, and so assuming it's not just supported on a periodic point, I want to say either it's supported inside the homoclinic class or on an odometer. Okay? So for that, I introduce a relation. So I take a full measure set of points for the measure, mu. And I say that X goes to Y if I have the following. So the closing lemma I've described tells you that X is approximated by some periodic point Qn. And I require that among this sequence of points, I can find some whose unstable arc will not only cross the stable manifold of X, but also the stable manifold of Y. Okay? Like on the picture. So this relation is transitive. let's assume x goes to y and that y goes to z. So you have y is approximated by periodic point Pn, and the stable manifold of Pn cross the unstable, cross both the stable of x and the stable manifold of curve of z. So what do you have? When Pn is close enough to y, its stable arc is very close to the stable arc of y. And now since Qn crosses the unstable manifold of Qn crosses the stable arc of y, it also has to cross the stable manifold of Pn. Okay? So Qn approximated x, but also jumps over to y, and then of Pn for large n. And then you apply what we call the inclination lemma or lambda lemma. So when you know the unstable manifold of a periodic point crosses the stable manifold of another one, then, so here the unstable manifold of Qn has to accumulate on the unstable manifold of Pn. And so if you look to the long unstable manifold of Qn, eventually it has also to cross the stable manifold of Z. Okay? So the X goes to Z for this relation. So you have transitivity of the relation. You also have invariance when you apply the dynamics. Okay. And so what to do with the relation now? So if you fix a point, now you look to all points that can be attained from the initial. So if you fix x, consider all the points y that you can reach by this relation. Okay. Since you have an invariance by the dynamics, this set related to x has some measure which does not depend on x. Okay. So it's some number. This number is either positive or zero. Okay, so you have two cases to consider which correspond to the two cases, homoclinic or odometer, that we will have. So for instance, when it is when the measure is positive, so from x, almost every point x, the set of points you can reach has a given positive mass. Okay. So the recurrence, eventually, the iterates of x will come back to the point that x can reach. And so you have a relation between x and a first iterate fn of x. Okay. And so when you play with that, you find that the set A of point that x reach, it's a set, it's disjoint up to measure 0 from its iterate up to this recurrence time. And so you have a decomposition of the measure into sets, iterates of A for a fixed number of iterate. Okay. So now I want to show that you have a homoclinic class somewhere. So consider a point x for the measure, and another point for the measure which is in the same set A. And then, well, since this set A has a positive measure, you have plenty of such points. So you can, and almost every point is accumulated both on the right and on the left by such point. And so let me introduce two more points. So we have 4 points whose stable manifold are almost parallel if I restrict to a good set with positive measure, so a Piècine set. So you have 4 points almost parallel, but x and y are in the middle, okay? And now I play with the relation, so knowing that, so x is accumulated by point Qn, periodic point Qn, but then the unstable manifold of Qn has to go and cross all stable manifold of the 4 points. And y is also accumulated by periodic point Pn, whose unstable manifold crosses all stable manifold for the 4 points. And just from this property, you see that the unstable manifold of Qn has to cross the stable manifold of Pn to reach the most extreme points. It has to cross the stable arc of the point in the middle. And so Qn, you have an heteroclinic orbit now from Qn to Pn, and for the same reason from Pn to Qn. And so the periodic points that approximate X and those which approximate Y are homoclinically related. And so they are in the same homoclinic class. So you have a single homoclinic class which contains all these periodic points approximating X and Y. And so taking the closure, it contains X and Y, which are typical for mu. And so mu is supported on this homoclinic class. Okay. So this is the first case. What about the other case? So when the set I have introduced has measure 0. So we try to do something similar. So you pick a typical point X. It's approximated by periodic point Qn. So fix one of them. Then you look to all the iterates of Qn and to its unstable manifold, and you look to what are the, for instance, if you fix the stable arc of X, which are the iterates of Qn whose unstable manifold cross the stable arc of X? Okay, so it's some data. And for other typical points for the measure, you look to points that have the same data. Okay. And in this way, you decompose the measure into PC that have different possible datas. And the species will be exchanged cyclically. Okay. When you consider a periodic point Qn which is closer and closer to X, its unstable manifold cannot cross many set with large measure of points because of the assumption. The assumption is that from X, there is no periodic point arbitrary close which can reach a set with arbitrary with measure not close to 0. So the decomposition I find from a periodic point Qn will get thinner and thinner when the point Qn has larger and larger period and get closer and closer to X. And so in this way, we can find cyclic decomposition of the measure with arbitrary large period. And so this is a way to find an odometer. Okay, so we have found the two cases. So then, I plan to have some comments about the proof, but it takes some time to enter in the proof. So I don't know. I don't want to. Maybe I have what? How many? 3 minutes?
Maybe 5 minutes.
Maybe 5 minutes. Yeah.
Okay. Well, I can say something and stop at any time. So just to try to give a bit a flavor of what we do, it's very topological, as I said. So the goal is to try to mimic the 1D proof. So you have a measure, you take a typical point, you take an iterate which comes close. So you have X, you have Y. But now you're on surface and you have the stable arc which separate the plane. And so you get a strip bounded by the stable arc at X and at Y. So assume the plane is mapped into itself. So you have you can work with a disk and then you find a bounded strip and you can compute an index around the boundary of that strip. And now you can take an iterate so that Y comes back to the left of X and X stays to the right of X, like on the interval. And for that iterate, the index around that curve is 1. And so it says you have a fixed point inside the strip. So it's very similar to dimension 1. But now you want more information, and what you would like is to find a periodic point whose stable arc separates x and y. And so when y comes closer to x, you get a strip which is thinner and thinner, and so the stable arc of the periodic point you find gets Hausdorff close to the stable arc of x. Okay. Okay, so this is what you would like. So the problem is that the periodic point you find may have a stable arc which is not separating. So you have different cases to consider. In some cases, the index you find for P here does not contribute to index 1 of the region, and so you know you have other fixed points. Okay, so there are fixed points you may exclude immediately for any index reason. There are others that you cannot exclude immediately, so you have to do some special constructions, some special surgery, but at the end do some index argument and eventually find a good periodic point whose stable arc is between x and y. And so that's the first part. You wanted a stable arc that approximates well in Hausdorff topology a stable arc of x. And then the second step is to show that the unstable arc P has an unstable arc which cross the stable manifold of x. Okay. And so then again, you come back to 1D. What did you do for 1D? You consider a further iterate so that so still fix P, but sends x to the left of itself. Okay. So you have the strip between x and P is mapped on the blue region here on the picture. Okay, so if you do that, you see that the image of the strip crosses the stable manifold of x, so it defines a subarc. And if you pull it back, you get an arc gamma 1 here on the picture, if you can read, which crosses the strip between x and P. And then gamma 1 cross the blue region by a subarc. You take its pre-image and you find a new arc gamma 2. And in this way, you have a sequence of arc gamma n, which separate the strip and which is ordered monotonically. And you want to take a limit. So you have a sequence of arcs ordered, mapped into themselves. So if you take the limit, you find a continuum, which is backward invariant. And so by a theorem of Cartwright-Littlewood, you should have a fixed point. So you know that this limit of curves has to accumulate on a fixed point. So maybe it's P, but maybe it's another fixed point. So you have to exclude other fixed points, again, by index reason. And when they accumulate, it forces P to have an unstable arc somewhere. And so some of the gamma n will cross the unstable arc of P, which say that, in fact, the unstable arc of P cross the stable arc of x if you iterate further forward. So to say something very short, but there are many steps to consider. Okay, so this is to conclude. We had this result, which is a beginning of something. So just to say, question: we have many homoclinic classes. A question you may ask is, what happened? In general, it's infinite. How do they accumulate? And so something you may look. For instance, Misha talked about periods. So homoclinic classes have period. Consider homoclinic class with a given period. Is this set finite? So does the period goes to infinity when you go over the whole family of homoclinic classes? So there are questions we want to address. Okay, I stop here. Thank you a lot.
Thank you. We have time for a quick question or two.
So how about the number of automata? So do you anticipate there could be infinitely many automata coexisting?
So this is something I don't. We cannot answer by the topological argument we have. So So even in the case of entropy zero, where we can say a lot about the way things are organized, we still don't know about the number of odometers. So in the more general case, we have no idea. You need to probably to add more quantitative arguments.
Some Newhouse type probably situation, yeah, Newhouse type analysis.
Yes, no, you're right. In the Newhouse, for Newhouse domain, you have uncountably many odometers. Yeah. You're right. We don't know in the zero entropy case. You're not in the Newhouse regime, and the number of odometer. It's a question we don't know if it's finite or not necessarily. But when you have Newhouse, you know that you have.
So you might have infinitely many.
It's uncountable. Yeah. Yes.
Okay.
Yeah. You're right.
I see.
Okay, I think Amy also had a question. No.
No, I was clapping my hand, but it,
Sorry.
Sorry.
Okay. Any other quick questions? Okay, let's thank Sylvain again.
Thank you. Thank you.
And we have a 6-minute coffee break. We'll
Okay,
resume in 6 minutes.
This needed.
Okay.
Hmm. Миша, где ваше кофе? Есть?
Вот.
Все в порядке.
Вот. Хотите,
Нет, давайте вы правда.
ну,
Продолжите.
что только я. Давайте ротацию сделаем.
Трудитесь, Миша.
Too much work.
Ты будешь Жекан. Жекан.
Jikan,
Да.
would you
Yes.
like to be in charge of the next talk?
Sure. Are we ready to go now? Okay.
Seems that it is time, more or less.
Yes.
Mhm.
Okay. So
The speaker is
Okay, so hello everyone. Our next speaker is Andrei Maronov. He's going to talk about integral billiards inside cones.
Okay. Hello. Thank you very much for the invitation. Are you hear me?
Yes.
Oh, very good.
Yes.
Okay. My talk is based on our joint work with Xiao Yin. So there are examples of integral billiards in plane and in the space, and in all known examples, billiard table is quadric or consists of pieces of quadrics, and in the space, in the integrable case, billiard table is conic and quadrics or consists of pieces of quadrics. And in our works, we show that if we consider cone over strictly convex variety, then the Birkhoff billiard inside such cones is also integrable. And our example doesn't relate to quadrics. So this is the plan of my talk. In the beginning, I give a short introduction, and after that, I explain our results. First of all, let me remind what is Birkhoff billiard in the plane. So let's assume that we have a domain in the plane, and we assume that we have a particle which moves inside this domain. When the particle reaches the boundary, it reflects according geometric optics law. The angle of incidence is equal to the angle of reflection. So for Birkhoff, as far as I know, for Birkhoff, it was very interesting to study the problem of existence of periodic trajectories. For example, if we take a triangle such that all angles less than pi divided by 2, then in such triangle there is a 3 periodic orbits. More precisely, if we consider heights A1, C, C1, and B, B1, then trajectory A1, B1, C1 is periodic, 3 periodic trajectory. Not difficult to prove that if we take smooth convex curve, then inside this domain there are n periodic orbits. To prove it, one can consider the length of n goal, and this length is continuous function on n torus, and to the maximum this function reaches the maximum, and the trajectory corresponding to this maximum is periodic. But Bergov proves a more deep result. He proves that if we fix also rotation number, then for the pair rotation number, then for every rotation number there is periodic orbit. And as far as from now, from this problem, Morse theory was appeared. Morse was a student of Bergov. Another very important notion is caustic. So let's assume that we have a billiard table, which is blue, and the red, the curve inside billiard table is called caustic. If you have the following: we take an arbitrary trajectory such that this trajectory is tangent to the caustic, and if after the reflection it is again tangent, then this curve is called caustic. Lazutkin proved the following remarkable fact. If the billiard table is convex and rather smooth, and if we assume that the curvature is positive everywhere of billiard table, then in the neighborhood of billiard table there are infinitely many caustics. Moreover, if we take union of this caustic, then the measure of this set is positive. Let's consider the simplest examples. If we take a circle, then every circle with the same center is, of course, caustic for this billiard table. And the billiard inside a circle admits the following first integral: xv2 minus yv1. X and y are coordinates of the particle, and v1, v2 is the velocity vector. Let's consider another example. Let's take an ellipse, x to the power 2 divided by a to the power 2 plus y to the power 2 divided by b to the power 2 is equal to 1. Then confocal ellipse, which is given by this equation, is caustic. And moreover, billiard inside the ellipse admits the first integral, which is degree 2 in the components of the velocity vector. It is given by this formula. And it is very natural question. This is Bergov conjecture, more precisely Bergov-Paritsky conjecture. It was formulated by in the paper by Paritsky, but he mentioned that it was considered by Bergov also. So let us assume that we have a convex billiard table, and let us assume that the neighborhood of the billiard table is foliated by caustics. Then the billiard table is ellipse. So this conjecture has not been proved yet, but there are some partial interesting results. The first type of results is related to the case when the billiard admits polynomial in components of the velocity vector first integral. So Bolotin proved if there exists such first integral, then the billiard table is an oval of real algebraic curve. And moreover, if we consider algebraic curve which is defined by the same equation in CP2, then this curve must be singular or billiard table is ellipse. Misha Bialy and me obtained similar result, but for dual algebraic curve. To prove this result, we used so-called angular billiard. And Alexei Glutsuk proved the Bergov conjecture under the assumption that there exists first polynomial integral. In the smooth case, I would like to mention also several results. First type of results belongs to the group of Vadim Kaloshin. They proved the following type of results. If you take some perturbation of ellipse in some functional class, then for perturbated billiard table, the Bergov conjecture is true. And Misha Bialy and me proved the Bergov-Parisky conjecture under the assumption that the billiard table is centrally symmetric. And we assume that the foliation by cosec is rather big. And now let's consider billiard in space. If you take ellipsoid in Rn given by this equation, then the billiard also admits cosec's which are given by this equation. So if you take a trajectory, then after the reflection, if the trajectory is tangent to the cosec's, then after the reflection, it is again tangent to the same cosec. And it is very natural question, is the analog of Lazutkin theorem true? It turns out that not true in general case. It was proven by Berger. He proves the following. If n is greater or equal to 3 and C2 smooth hypersurface gamma with non-degenerated second fundamental form admits a C2 cosec with non-degenerated second fundamental form, then gamma must be a piece of quadric and the cosec must be a piece of confocal quadric. So this is Berger theorem. And I would like to mention that the assumption that the second fundamental form is non-degenerated is very important in this theorem. Okay, and now let me explain our results. Let's consider a cone over variety gamma. So let gamma be some variety in the plane xn is equal to 1. And let's consider a cone over this variety gamma. So this is just definition the cone. Then it turns out that the billiard inside this cone admits very natural first integral. But before formulate our theorem, I would like to ask a question. What do you think? If you consider a billiard trajectory inside this cone, how many reflections can have the trajectory, finite or infinite?
So let us see, when you're saying inside the cone, you mean in the plane or mean just in the space? So, well, in this hyperplane or it is
Of course, in the space.
in the space.
Yes.
Mhm.
So let's consider the trajectory inside the cone. It is a very natural question. How many reflections, finite or infinite?
So when it is final, then it would escape to infinity, the trajectory. That is what is supposed to happen. Or,
Yes.
so, or yes, that is a scenario with finitely many, escaping to infinity.
Actually, it depends on smoothness of gamma. Now I will formulate our result a little bit later. So let's introduce the components of the angular momentum, xy vj minus xj vi. Then the Birkhoff billiard inside K admit the following first integral. We take sum of square of these components. Then now this is the first integral. And this first integral has a very interesting geometric meaning. This is the first statement. And the second, the sphere centered at the vertex O of K are caustics of the billiard inside K. It is lines containing the segments of the trajectory are tangent to the same sphere. So we have the following picture. If we have billiard trajectory, so this line is tangent to some sphere. Then it's shown out that after the reflection, the trajectory again will be tangent to the same sphere. So this means that these spheres are caustics for the core. And we have that the analog of Berger theorem is not true in this situation. Let me remind the Berger theorem. In the Berger theorem, it is assumed that the second fundamental form is non-degenerated. And this condition is important here. For Coulomb, it is not true. And this integral is just squared of the distance from origin to the trajectory. So this is square of the radius of this sphere. And let me recall you Sinai theorem. Sinai considered a billiard trajectory in a polyhedral angle in Rn, and he proved that every trajectory in such polyhedral angle has a finite number of reflections, always. And moreover, there is a uniform estimate for the number of reflections for all trajectories of fixed polyhedral angle. So the number of reflections can be estimated by the same constant, and this constant depends only this angle. In the plane case, it is very well known. So if we have an angle of measure theta, then every trajectory has at most the smallest integer greater than or equal to pi divided by theta. For example, in this picture, every trajectory can has one reflection or two reflections. On this picture, two reflections or three reflections, and similar here. And now let me formulate our first result. Let us assume that variety gamma is a strictly convex closed hypersurface with non-degenerated second fundamental form. Then if K is C3 smooth cone, then any billiard trajectory in K has a finite number of reflections. And there are convex C2 smooth cones with billiard trajectories having infinitely many reflections in finite time. So The second part of its theorem is an analog of famous Halpern theorem. Halpern construct a convex C2 curve in the plane such that inside this domain bounded by this curve, there exists a trajectory which has infinitely many reflections in finite time. And here there exists the similar phenomena. So let's consider the simplest examples. Let's take an elliptic cone in R3, which is given by this equation. Then the billiard admits two first integrals. One is our integral from theorem 1, and additionally it has this second first integral. And it's to note that we can estimate the number of reflections, but for this we have to fix the values of these first integrals. So the number of reflections of trajectory inside elliptic cone with fixed values of the first integrals, A1 is equal to C1 and I2 is equal to C2, is bounded by this number. Of course, if we fix only I1, then the number of reflections can be arbitrarily big. But if we fix also the second integral, then the number of reflections can be estimated by this formula. So now I would like to explain that the billiard inside such C3 convex cone is integrable. To do this, let's describe phase space. So the space of oriented lines is diffeomorphic to the tangent space to unit sphere. Indeed, if we have oriented line, we can assume that the direction vector has length 1. Then to oriented line we can to this line we can be corresponded the pair unit vector v and the point q, which is the shortest, which is the point on the line which realizes the shortest distance between O and the line. So we get tangent space to the sphere. So this is the space of oriented lines. And phase space of our billiard system is a union of three subspaces: psi minus, psi, and psi plus. Psi minus is a set of oriented lines coming from infinity and intersecting the cone once. This is on the first picture. Psi is a set of oriented lines intersecting the cone twice, as in this picture. And psi plus is a set of oriented lines intersecting the cone once before going to infinity. So our phase space is a union of these three spaces. And it's turned out that the whole phase space and psi minus union psi and psi union psi plus and psi are open subset in the tangent space to the sphere. And of course, billiard map from a union of psi minus and psi into psi to psi plus if is diffeomorphism. And it is very natural to extend our billiard map from psi to psi. If L belongs to psi minus to psi, we of course assume that mu of L is mu small of L. And it is very natural to assume that mu of L is equal to L if L belongs to psi plus. So if oriented line doesn't have intersection with the cone, as in this picture, with blue line, of course, we must assume that mu of L is equal to L, because L doesn't have reflection with the cone. And this Billiard mapping, extended Billiard mapping, is not continuous. It can be demonstrated on this picture. So let us assume that we have oriented line, which is blue on this picture. This oriented line is parallel to a generatrix of the cone. And if we have a sequence of oriented lines such that this sequence tends to this blue line, one can see that mu of xn tends to the red oriented lines, and these red oriented lines doesn't belong to phase space. And from here it follows that unfortunately this extended Billiard map is not continuous. Okay, but we can construct a continuous first integrals of the Billiard map mu. To do this, we have to study the behavior of our extended mapping. The difficulty is the following. Let's take a point on psi minus such that after several point x, such that after the several reflections, it maps to the point on the boundary of psi plus, as here. And if you take a neighborhood u of this point, then after several reflections, we obtain this picture. So a part of the neighborhood of point mu n of x belongs to psi, and another part belongs to psi plus. And after the next iterations, the below part of the neighborhood is fixed, but upper part maps to the another part of psi plus. And to construct continuous first integrals, we must to understand when the value of the first integral in the red point coincides with this point. This is the main difficulty, and this is requires some analysis. We can describe the boundary of psi plus. It consists of two parts. One part is delta zero. Delta zero can be defined by the following formula. It consists of pairs VQ, where V belongs to gamma. Gamma is the intersection of our cone with a unit sphere. And NV is inward normal vector to the cone in the point V. And delta zero is defined by the condition scalar product of NV and Q is positive. So delta zero belongs to the boundary of psi plus, and at the same time, this set belongs to psi. And another part of the boundary, delta 1, is described by this formula. And let's define a mapping from delta 0 to delta 0 cone. So let's take arbitrary point on delta 0, and let's consider a sequence of points z which tends to x0, x to this point on the boundary. Sequence z belongs to psi. And sigma of x we define as a limit of mu of z. So this maps, this point, blue point, is mapped to red point. And this mapping is defined by this explicit formula. So sigma on VQ is equal to VQ minus 2 scalar product Q and V and NV. It can be calculated by hands. Now we can construct a first integral. So if we not require continuous of the first integral, continuity or smoothness, it can be done by the following formula. Let's take arbitrary function, and we can define a lift of this function to the whole phase space by the following formula, where m of x is a minimal non-negative integer such that mu to the power m of x belongs to psi plus. So we know that every trajectory after several reflections belongs to psi 0, and m of x is a number of reflections. And this is the definition of a function on psi. And of course, it is first integral, because this function is constant on arbitrary trajectory by the definition. And here, of course, we use the property that every trajectory has finite number of reflections. The more interesting question, when this function is continuous or smooth. So let f be a function from psi plus to r, and let it be a continuous function. This function can be extended to the psi union delta 1 0 by this formula. So the value of extended function in the red point is naturally defined, can be defined by this formula. We take sigma to the power minus 1 of this point and x, yes. And here we know the value of f. And now we can formulate a criteria when lifted function is continuous on the whole phase space. So function f is continuous on psi plus union delta 1 0 if it continues here. Then the lift f tilde is continuous of the whole phase space. So to understand if f tilde is continuous on the phase space, it is necessary to understand if the extended function is continuous on psi plus union delta 1 0. And now we can consider examples. Let's take our first integral, which is constructed in the first theorem. So this is, let me remind, I is a square of distance from origin of the cone to the billiard trajectory. So this integral on the oriented line VQ can be calculated as scalar product Q of and Q. And this function satisfies the continued criteria. So if you take oriented line from delta 0, then what we have? I of sigma VQ, which by definition is given by this formula, scalar product of this vector and this vector. And by explicit calculation, one can check that it is equal to a scalar product of Q and Q, and it is equal to IVQ. So this calculation shows us that I is a continuous function on the phase space. From geometric point of view, it is obvious, but this analysis show how to apply this criteria to a concrete example. And another important example of continuous first integral is the following. As I explained, every trajectory has finite number of reflections. Then every trajectory has end vector. So the direction of the oriented line, which has no intersection with cone. Let's V be this direction. Then by our construction, the components of this velocity vector extends to the V plus union delta 1 0. And this extended function satisfies this criteria. No, it can be shown on this picture. Where is it? On this picture. So limit mu of xn has the same direction vector as blue oriented line. And hence, if we take a lift of these components to the phase space by this criteria, these functions are continuous on the whole phase space. Moreover, these functions are smooth almost everywhere. And now I can formulate our next result. The billiard, Bergov billiard inside cone is super integrable. So this means that there are continuous, smooth, almost everywhere first integrals I1, I2 and minus 1, which coincide with our first integral I. These functions are invariant under our extended billiard map mu capital. And moreover, we have the following property. Each point in the image of the map, which is defined by these first integrals I1, I2 and minus 1 from psi to R2 and minus 1, determines a unique billiard trajectory in psi. So roughly speaking, if we fix values of our first integrals, then the values of these first integrals define uniquely our trajectory. And moreover, I didn't formulate it here, one can construct smooth first integrals such that billiard trajectories can be defined by various, almost all trajectories can be defined by smooth first integrals. But the values of smooth first integrals do not define all trajectories, only almost all. And moreover, this billiard system is completely integrable. Let me explain what does it mean. So the phase space psi capital carries a natural symplectic structure inherited from R2n with a standard symplectic form on R2n. So phase space is identified with an open subset of the symplectic submanifold psi zero. So our tangent bundle to the unit sphere is defined by these two equations in R2n. First equation means that the velocity vector has length 1, and the second equation means that we must take a point from the tangent space. And our phase space is open subset of this psi zero. And we can restrict a standard symplectic form from R2n to this open subset. And we have symplectic form on our phase space psi capital. And to prove complete integrability, we can find explicitly Poisson bracket, which is generated by this symplectic form omega. And this Poisson bracket is defined by a famous Dirac formula. So if we have two functions f and g, then to calculate Poisson bracket on psi, we can take Poisson bracket of standard Poisson bracket and take different with this tail. And what we have? The extended billiard map preserve symplectic form omega. And if you take lift of these velocity vectors v1, vn, vi tilde, one can check explicitly using Dirac formula that Poisson bracket of vi tilde with vj tilde is equal to 0. It can be checked by explicit correlation. Of course, this standard Poisson bracket is 0, and these both terms are also 0. So vi tilde and vj tilde are Poisson commute. And one can check that first n minus 1 components of the lifted velocity vector are functionally independent almost everywhere on psi capital. Hence, we get that billiard inside cone is completely integrable as a discrete time Hamiltonian system. And as I said in the beginning, as far as I know, this is first example of integrable Bergov billiards when the billiard table doesn't relate to quadrics. Of course, billiard inside ellipsoid and another quadric is integrable. But here we have new phenomena. And main reason of this is that if you have C3 cone, then every trajectory has a finite number of reflections. Of course, here the situation is not the same as in usual billiard, because in usual billiard every oriented lines after several reflections can be infinitely close to first one. Here we do not have this phenomena. It's something different, but formally we have integrability. And maybe in the end, I would like to say that there is very interesting connection between billiard inside cone and geodesic flow on the cone over arbitrary Riemann variety. So in this case, the geodesic flow has very similar first integral, as I mentioned, for Birkhoff billiards. So if gamma of S is geodesic on such cone, then one can check that this first integral is the first integral of the geodesic flow. And this integral is just restriction of the billiard integral to the tangent space to the cone. And moreover, if you take arbitrary Riemann variety by Nash theorem, it can be embedded in some hypersurface in R big Rn, n is rather big. And if you take a cone over this variety, it turns out that geodesic flow on such cone is also integrable. So we have the same phenomena as for billiard inside cone. Okay, let me stop here. Thank you very much.
Okay, let's thank the speaker.
So for usual completely integrable Hamiltonian systems, we have this picture, Arnold's picture, foliation by torus and quasi-periodic motions of the torus. So can your situation be described in these terms, like some kind of suspension over this kind of quasi-periodic motions, or something in the spirit of this completely integrable?
So as far as I understand, the situation absolutely the same as when in the continuous case. Here we have discrete type Hamiltonian system, and
but your phase space is not compact, true? So it is kind of
it's not compact. It's not compact.
so somehow instead of tora, you should have some suspensions over the tora, I guess. Yeah. You have everything very explicit. Probably it is very. You have a very explicit picture of this integrability phenomenon.
Free space here is open subset of tangent bundle to sphere.
Yeah, but again, unbounded tangent unit tangent bundle to the sphere, and then not.
No, it's not unit tangent bundle.
Just tangent bundle to the sphere.
Tangent bundle, yes.
Unbounded. Yeah.
Point on sphere corresponds to the velocity vector of oriented line, and point on the tangent plane corresponds to the point on oriented line, which gives us the shortest distance between origin and the line. So it is not bounded.
No.
Any other questions?
So, but still, there is no clear picture of this geometric picture of this integrability at the moment.
In the superintegrability, the picture is clear. The values of first integrals defines the trajectory uniquely.
Yes, but it
Here, if we fix the direction
but
of the velocity vector,
but it
which is
is
parallel to generatrix of the column, we have rather complicated picture. A rather complicated picture of the trajectory with the same ending vector.
okay. Thank you. Yeah.
Any other questions?
Actually,
Okay.
just for education. So sorry. So is there any theory of the billiards in polyhedra? So like in 2 dimensions, there is a rich theory in polygons, and is there anything in 3 dimensions?
Unfortunately, I know only result of Sinai, which I explained.
Okay.
Okay. Let's thank Andrew again.
Okay, thank you very much.
So let's have a 8-minute break for coffee, maybe.
All right.
So maybe we should test the slides first.
Sure thing. Hold on a second.
Okay, looks good.
Can you see my slides?
Yes. Yes.
Great.
Okay. The desktop for now.
Oh, really?
Okay, no, it's good. Probably my
Okay.
internet is a bit slow.
No, that's all right. How do I make it? There's a. Oh, is it better like that? Yes.
Michael, do you want to the floor?
Which Michael? Me?
Michael, yes.
Okay, sure. Shall we start? Okay. So it's my pleasure to welcome the next speaker, Selim Ghazouani from University College London, and he'll speak on speculations about parabolic dynamical systems.
All right. Thank you very much for the introduction and for the invitation. It's a pleasure to talk at your seminar. So before I start, let me just say that I'm very happy to be interrupted and being asked questions. So feel free to go ahead and make comments, ask questions. That's yeah, I appreciate that. So the way I've sort of split the talk, I've split it in 3 parts. I'm going to start with an ergodic theory warm-up. So I understand there are a lot of specialists in the room, so it's more aimed at people that are not, very familiar with a lot of themes, and that's just a way of setting up notation and the way we think of things. And as we'll part 2 and 3 will be a bit more specialized and technical. Okay, so I'm going to start with what is technically more probability theory, but just remind everyone of the law of large numbers. So this is a very basic statement in ergodic theory. So you take a sequence of IID random variables whose expectancy is less than infinity, and then the average almost surely converges to the expected value. So this is a formal statement. Obviously, what you should have in mind is that you're flipping a coin and you're betting on the outcome of the coin toss. And let's say I is the ith coin toss and coin toss. Terrible. And you gain 1 if it's heads, and you lose 1 if it's tails. So xi is equal to plus or minus 1 depending on the outcome. And so this just says that with probability 1, on average, you do not lose nor win. The average is essentially 0. Okay. So another way of reformulating this is, in this particular case of the coin toss, when the expected value is 0, is that this big sum there, when you've not averaged it, grows slower than linearly. And so I think this is quite a nice way of putting it, because when you play an actual game of coin toss, you will often find yourself that after playing a lot of times, you're nowhere near 0. You've lost a lot or you've gained a lot. The only thing is that it's much less than the number of times you've played. Okay, and so the second big theorem in probability is the central limit theorem, that sort of makes a bit more precise the amount that you will have lost or won after doing so many coin tosses. And if you've not done any probability, the statement of the central limit theorem informally essentially tells you that if you take something of 0 average, you do n experiments, well, what you would get is roughly of the order of square root of n. This square root of n is the important bit in the central limit theorem. And the formal statement of the central limit theorem is the following. So if you know probability, you will have noticed that I missed an hypothesis, but I don't want to overcrowd the statement, so I'll stick with that. So if you take this sum and you renormalize it
So, sorry, in the hypothesis of the theorem, you should also have that the expected value of your random variables is 0 all the time. So if you renormalize it at the scale at which you think it's going to grow, then it converges in law towards a Gaussian distribution, basically. So I'll get back to, the precise statements when we'll move back to dynamical systems. So I just wanted to state the central limit theorem as a bit of a warm-up. All right. So now I want to explain to you how, thinking probabilistically helps in dynamical systems. So when you do dynamical systems, you want to recreate some formal framework which resembles probability. So if you take a dynamical system, which in our particular case, I think of as a measure preserving system. So you have a measure, you have a map. Maybe I assume that my map is a bijection, continuous, whatever. And then I take a function f here, which I think of as an observable. So it's something that gives me some information about where I am in x. For instance, you could think of, you take x, you cut it in half, and this function f is 1 if you're in one half and 0 if you're in the other half. And it just tells you, if you are in which bits of x you are. So get back to this in a moment. And so now when I look at f, which I will have composed with ti, this sort of tells me something about where, if I start from a point x, I've landed in my space. My space, I can think of it as a manifold, right? So, and this, I can think of it as a family of random variables, if you think probabilistically. And the only difference with basic probability theory is that they're not independent. And, because if you know where x was at a certain point, then you have some information about where it'll be in, 3 or 4 iterations time. Okay, so that's the main difference. Now, if you've done a bit of ergodic theory, when mu is ergodic, you've got this theorem, this called Birkhoff's ergodic theorem, and in this context, you see that it's formally a generalization of the law of large numbers to a case where your random variables are not necessarily independent. Okay, so that's sort of how I think of it. Anyway, all right. So now, if we do dynamical systems, I just want to remind you of a general class of dynamical systems that I'm not going to define formally. Sylvain did a bit of that in his talk, and you've got many sort of different definitions of hyperbolic that are competing, but all things that people tend to call hyperbolic have this common feature that when you compute the derivative, it looks like a matrix that is diagonalizable, or at least the eigenvalues are either larger or less than 1. And you get some form of expansion or contraction in some directions. So instead of giving formal definitions, I can just take these 3 examples, and that will be enough for what I want to tell you. So either you take the doubling map on the circle, or you take, maybe that's my favorite example, the Arnold's cat map, which is something defined on the 2 torus by this formula. So I presume a lot of people have seen this. And otherwise, if you're happy to work with flows, you can take the geodesic flow on a negatively curved surface, hyperbolic surface. Okay. And so there's one of the reasons why this category of dynamical systems is so interesting is that, or at least it can be analyzed, is that when you do statistics with these things, there's this general sort of meta phenomenon that probability theory emerges when you start doing statistics. Okay, so again, I'm sure a lot of people are very familiar with this, but if you've not seen it, that's the opportunity to look at this. So I'm going to tell you how I think of, so we've seen that we have the law of large numbers. So now I'm going to see what it would mean that a central limit theorem holds in this context. So I'm going to take the cat map now. I'm looking at this map. I'm taking the 2 torus, so I think of it as this square where I've glued opposite sides together, and I cut it in 2 halves of equal volume, x plus and x minus. And I'm basically going to use these 2 halves to emulate a coin toss. I'm going to take a point, that's what the game that I'm going to play, at random on the torus, and then I'm going to iterate my map, and I'm going to, let's say, win one mu rho, if you like, when I'm in x plus, and lose 1 when I'm in x minus. Okay, so that's what we do. So formally, I take the sequence epsilon n, that's 1 if I'm landing in x plus, and minus 1 if I'm landing in x minus. The central limit theorem, again, the informal version of it, will tell you that if for a random choice of x, this sum is going to grow like square root of n. Okay, really, I mean, if you can't absorb the statement of the standard central limit theorem, that's probably the first thing that you should remember. All right, and okay, so if you want a more formal statement, you take a hyperbolic dynamical system, so let's say the cat map, which preserves, so it works for most measures. In the case of the cat map, you've got the Lebesgue measure that's invariant, so it works in this case. And you take now any observable that's sufficiently regular, zero average with respect to the invariant measure. You take those Birkhoff sums. So now you think of this thing, this sum, normalized sum, as a function. So it takes a point and it spits out a value. And you can, when you have a function like this on a space, you can look at the law of this function, which tells you the distribution of the values that it takes. And so the central limit theorem tells you that it converges to a normal law. So it's a law, its distribution is Gaussian. So I'm just saying a few more words about this because, I don't know, when I was learning this, I always found it difficult to think in terms of law. So when I take this function, I can look at the set of points in my space. So x in our case is probably the 2 torus. And you look at the set of points for which this sum lands in AB. So this function may well be very, very ugly when you look at it as a smooth function because the derivatives of tj are exploding. But if you look at the distribution, there's the measure of the set of points that take a value in a given interval, it's given by the integral of a nice function that is this Gaussian distribution. So that's what it says. If you want to think of it in more probabilistic terms, you can also say that if you fix an interval, the probability that this sum lands in this interval is given by the integral of this function. Okay, so there you go. So that was it for my sort of introduction. That's what I want you to have in mind. And so what we're going to try and apply this circle of ideas to a class of dynamical systems that some people call parabolic dynamical systems. All right. So before I start with this second part, does anyone have any questions about this little introduction? Okay. Well, I'll continue on then. All right. So I'm going to start with this, let's say, weird comment at this stage. If you look at matrices in SL2R, you can decompose them into 3 types, right? You've got what people often call hyperbolic matrices, those that are diagonalizable in some basis, and for which I forgot to say here, but I think of this lambda to be larger than 1, say. Then you've got rotations, and then you've got this one sort of less standard class that is unipotent upper triangular matrices with 1s on the diagonal. Okay, the reason some people tend to forget the third type is that if you partition SL2R into these 2 types, the first 2 types of matrices, they cover an open set of full measure, and these ones are sort of exceptional, and you can often ignore them in many problems. All right. So the reason why I'm saying this is because we're going to use this to somewhat very roughly classify smooth dynamical systems. If I take a dynamical system, and again, there's nothing rigorous here, I'm being very loose, but it's just if you go look in a book, you'll have formal definitions, then they will use this idea as a basis for their definition. But a dynamical system is called quasi-periodic when the derivative is essentially of the second type. So it's a rotation. When you take iterates, it stays within a compact set, and when you take 2 nearby points, they tend not to drift apart, away from one another. Okay, and so most examples reduce to translation on Torai, and if you've heard this keyword, like it's the realm of KM theory. All right, so that's one world, sorry. And then you've got hyperbolic dynamics that, again, we've mentioned briefly earlier and can often be defined by the non-vanishing of some quantity called the Lyapunov exponents. They have a nice property that they can be stable, and from a purely statistical perspective, when you have a hyperbolic dynamical system, the probability theory tends to sort of emerge via, I don't know, Markov partitions or whatnot. Anyway, so the third category that I want us to look at today is what, so I don't think there's clear definition of what it is, but what I want to call parabolic dynamics, which are those dynamical systems which would be neither hyperbolic nor parabolic. Now, how to define such things is, I suppose, up for debate. You could say, you know, in order to have something that is completely exhaustive, that you assume that Lyapunov exponents, whichever way you want to define it, are 0. That's quite weak because somehow you could imagine some sort of crazy dynamics where the derivatives grow very fast but still sub-exponentially. You could also say that, well, I really want to force my derivative to be, so I said unipotent here. What I mean is really some matrix with only ones on the diagonal and maybe some upper or lower diagonal coefficients, or maybe something in between, which would be if you take two nearby points, then they drift away from one another at polynomial speed. Okay, so anyway, I'm not going to attempt to give a formal definition. I'm just going to try and study examples in what follows. So I'm giving you what I think are essentially 3 of the nicest examples that you can work with in terms of the parabolic dynamical systems, because a lot of the phenomena that you might be interested in can be observed on these cases, but they're sufficiently simple to be described. So I'll start first with Torai's Q products, when if I take a map of the form XY maps to, so there are 2 different ways of writing it. In order to define it, it's easier to say it's the map x plus alpha, y plus x. Now I like to write it in its affine form there because obviously there you can see that the derivative of the map is this matrix, and you immediately see that when you start iterating this map, the derivatives, they do not grow too fast, right? Because when you iterate this map, this is going to grow linearly, right? The diagonal coefficient are not going to change, and the upper lower diagonal coefficient is going to become n when I've iterated n times. Okay, so I'm going to jump straight to the third one because I'm just saying here that you can do the same construction in higher dimensions. You stick a unipotent matrix here, plus some translation. The translation doesn't make any difference, and you get something that has the same flavor. There you go. And maybe the third example, which is important for many other reasons, is the horocycle flow on a hyperbolic surface. So I'm sticking with diffeomorphisms here, but you could take the flow if you wanted. But if I take the action of this matrix, 1, 1, 1, 0, on the left on any quotient of SL2R by some co-compact lattice, so you will have recognized maybe the unit tangent bundle of a hyperbolic surface, then you get something that is also parabolic. I cannot really prove it to you. I'd have to compute the derivative. It involves a bit of Lie theory, but take my word for it. All right, so these are concrete examples. So again, so this is pretty standard. All the examples that I've given you there, they're all uniquely ergodic in that they have only one invariant measure, which is going to simplify the discussion immensely. And in all these cases, the invariant measure is essentially the Lebesgue measure in some sense. I'm going to go back. In the case of this Q products, things that I call Q products, the invariant measure is just the Lebesgue measure on T2. Or take the measure on R2, you project it down to the quotient by the action of Z2 on, well, and you've got there. And in the case of the Hall cycle flow, it's just the Haar measure, if you know what it is, or the Liouville measure, if you prefer thinking in terms of Riemannian geometry. Anyway, so at any rate, in the class of the Lebesgue measure for measures. And so in this case, if we want to think in terms of statistics, well, the ergodic theorem applies, and it will tell us, so I would like to write it this way, that's why I presented the law of large numbers this way, that's the Birkhoff sums of some average zero observable grows sublinearly. Okay, little o of n means that it's a quantity that when divided by n is equal to tends to 0. Okay, so now it seems reasonable to ask ourselves, what happens at the second order, the order where you observe in the probability theory in hyperbolic dynamical systems, the central limit theorem. Okay, so in particular, you can ask yourself, when I take those Birkhoff sums, to which extent do they look like independent, identically distributed random variables? Okay. So here I just want to mention that I'm aware of the fact that there are a lot of partial results on these questions. I don't want to bomb you with a lot of results. First, what I want to do is that we look at numerics to get a sense of what can happen. Okay, so what I'm going to do here is I'm going to take 4 different examples of such dynamical systems. So, because it's easy to do numerics with these guys. So I'm going to take the first Q product. For alpha here is going to be the golden ratio. It would work for any irrational number, but still. Then a higher dimensional example, so on T3. Then I'm going to take this thing, and I'm not giving you the formula, but I turn it into something nonlinear by adding some small perturbation that keeps it parabolic. And, for good measure, we still want to compare this to a sum of random variables, so I'm going to plot same as sum of such random variables. So, okay, I'm going to do the following thing. I don't know if it works as well online that it works in person, but I'm going to show you the graph that you get when you do the numerics of these 4 without telling you which is which. And so we can sort of observe and see if we can see a pattern and then disclose which is which. Okay, so there are 4 of them. So there we go. So that's the first plot. So I think I did some, I should have tidied this up a bit. So here I've plotted about 1 million iterations. So this is the plot of the Birkhoff sums up to time 1 million. So I don't know if that makes sense. If I take the point, coordinate n, then I've plotted the value of the Birkhoff sum at this time. So it's a time-dependent picture. Okay. So this is one. This is a second one. Okay, so they look somewhat similar. This is so what I wanted to say, so it's about 1 million and the magnitude is about 600. And in this case, I think it's 100,000 and the magnitude is 200. In this case, it's still 100,000 and the magnitude is 50. It's still about the same. So I'll have you notice that plot 3 looks a bit different from 1 and 2. It has a slightly different structure, a bit more orderly. And that's plot 4 again. And so here we're looking again at 100,000 and the magnitude is roughly 50 or thereabouts. Anyway, so that's what you can see. So I don't know if you want to see them again, I'm showing you. Okay, the first thing I'm going to say, you'd have to look at it in detail, and you can go much further in the analysis. These sums, they all grow like square root of n to begin with. So that's very similar to what we would see in probability. Now, one thing that was different, though, is that 3 of them, they look similar. Now, if you've played with these things, you will probably recognize picture that look random, maybe like the graph of a random walk or the Brownian motion, and there was an outlier that looked far more orderly, And if you think of the graph that you saw, so that was this one, looks a bit like a self-similar fractal, where if we were to zoom in, maybe we would see, the same shape again and again. All right. So now, yeah, I'm going to disclose which is which. So the first one was a sum of random variables. So that's sort of a, what we want to compare things to. So that's, good to have in mind. The second one was the three-dimensional example, skew products. So the third one was the one that was very orderly, and this one was the two-dimensional skew product. So this one is a bit different from the others. And the last one was some non-linear version of the second one, where there was a perturbation. Still looks somewhat random. All right. So, okay. So now I said, I'm not going to bomb you with theorems, but there is some work on some of these maps, and that one map that behaved a bit differently, if you're still with me, but so it was x plus alpha, y plus x. It's been proven by Griffin and Markloff that indeed, when you take the Birkhoff sums on average 0 observable, then it grows slow, at most like square root of n. So there's a definite constant, so that if you take any point, these stay less than c times square root of n. So in other words, if you were to renormalize this sum by square root of n, everything would stay bounded. So we'll comment on that a bit later. This is, if you've done enough probability, you would see that this already sort of contradicts the central limit theorem, but I'm not going to say much about this. For the other examples, well, the other dynamical examples, because we understand the random variables quite well, there aren't any bounds like that are well known, so this is widely open. The only thing that you can get rigorously are bounds on average. If you take the L2 norms of these functions, these Birkhoff sums, consider them as an average, then they grow like square root of n. Okay. Yeah. So anyway, so now to get a sense that the next thing to look at, if we want to understand whether some version of the central limit theorem can hold, is to try and understand the laws, the distribution that you get when you do your dynamics. So now I'm going to try and explain the experiment that I am going to show you, which is that you take one of those parabolic systems. Again, we're going to do a shorter list. You take some observable. So every time I do some numerics here, I take something very simple, the cosine of some variable or something, which is obviously of mean 0. Okay. Now, in order to get a good picture of a limit law samples over all points. So what I've got to do is take a large number of initial conditions that somehow fill my space. So I take a lot of them, and I have to compute all the values of the Birkhoff sums computed at those points, and then see the distribution that I get. So I get a lot of values for a very large time, fixed for the same for all the points. So now it's no longer a time-dependent thing that I'm going to plot. I'm going to fix the time and compute for many different points. And then I plot these values into a histogram, and what I should see is some approximation of the limit law. That's the limit law. That's what you get, right? So again, for one of those, I see this very odd limit law. So this is, I don't know how many things, I think it's probably 300 points up to time, I think 10,000, so it should be pretty reasonable in terms of approximation. And so this doesn't look, when I say normal, it doesn't look like a normal distribution at all. Okay, just wanted to point this out. And again, the culprit is the two-dimensional skew product. So that was the one that already looked a bit odd when we were looking at Birkhoff sums. All right. Now, if I do another map, so here, if you could please ignore the orange and green part, they're a picture of the same experiment for slightly finer spacing for the histogram. So just look at the blue thing. But in this case, you see the blue thing, and you've already seen a Gaussian distribution. Well, this looks very much Gaussian. Sort of get some something to approximate it. So like the central limit theorem. And so what's amusing is that this case is the three-dimensional thing, which on the face of it looks pretty much like the other one, but when you look at the dynamical properties, they're very different. All right. So we've seen, so I'm going to focus on this guy, x, y maps to x plus alpha, x plus y, seem to really fail to satisfy all the laws of probability theory. This is, I think, convincing. We've seen first that the graph, I'm going to probably go back to the graph once, was this one. It really doesn't look like the graph of a sum of random variables, which seems like very much random. There's far less structure. And the second point is, yeah, this limit law, right, which really doesn't look like a Gaussian distribution. All right. So this fact is somewhat well known from the work of several people. There, I don't really know the literature really well. I mean, there's a body of work. I don't really know who proved limit laws first and described them. So I'm going to say Markov, some co-authors, and Flaminia Forni. They've shown that for some things, for this map, and also for the horocycle flow, the limit laws are unlikely to look like what you get in probability theory. And the standard central limit theorem is unlikely to hold in these cases. All right. And so their proof essentially exploits the fact that these things, these dynamical systems, they happen to be the dynamics that you get if you follow the unstable manifold dynamics of some already hyperbolic dynamical system. And so for this reason, I'm going to call them self-similar, because there is some structure that is sort of forced by the hyperbolic dynamics that's underlying the picture. So for the horocycle flow, the hyperbolic dynamics that corresponds to it is the geodesic flow of the associated manifold, if you want to think in terms of, very general terms. And for these Q product maps, you'd have to look at what people call automorphisms of nil manifolds. So yes, I'm not going to... There is a hyperbolic dynamical system, and you could construct it. I'm very happy to tell you more about it if you're curious about this.
But in what ways these parabolic examples are related to these hyperbolic systems? So it is.
So sorry. So if you have a hyperbolic dynamical system, you will have some unstable dynamics, which might be a foliation. In this case,
it is the holonomy dynamics. That's what you mean?
Yes. So in this particular case, so I'm going to give you a precise statement. There is a manifold, a three-dimensional manifold, a partially hyperbolic dynamical system with only one unstable direction. So this unstable direction generates a foliation, and this map is the first return map of this foliation on some surface which happens to be a torus.
It is the holonomy dynamics, yes.
So it's the holonomy dynamics, yes.
But still, it's kind of usually we think of, I at least naively think of the holonomy dynamics as tremendously different from the original hyperbolic dynamics. Why it should inherit any hyperbolic features? So it is.
You're absolutely right. It doesn't inherit any of the hyperbolic features, because if you were to think about the dynamics there, the dynamics of your hyperbolic dynamical system in terms of ergodic theory, what you get is essentially the central limit theorem. And in these cases, you don't have the central limit theorem.
Misha, I think the point is that Salim's saying exactly the opposite, that because this is the stable, it shouldn't look like a random IID, but the others are not.
Yes,
I think
absolutely.
That's
I mean, you're absolutely right. It's a bit unfortunate that somehow the hyperbolic. So you have the examples of hyperbolic dynamical systems that do satisfy the central limit theorem, and we can forget about them. And now you have hyperbolic dynamical systems that have unstable foliations that generate some dynamics, and these ones do not satisfy the central limit theorem.
That is natural. That is natural, yes. This
Uh,
should not, but there is still the square root of n order of deviations. It's also
absolutely, absolutely. So this is quite. I'll say a few words about it in a bit. So you're absolutely right. So okay, now maybe emphasize this point. Misha's right. Still, even when we don't have the probability theory, the right scale at which to renormalize things to see things is square root. And this seems to be far more universal than just probability theory. So there's a reason for that. There's a mechanism. I probably won't have time to describe it in detail, but we'll do a calculation in maybe 10 minutes time that at least will probably shed some light about the phenomenon. So bear with me one more second. Okay, so I'm going to move to part 3 anyway. If there are other questions, I'm very happy to take them now. Especially that, sort of the things that I'm going to say now sort of build on what we've just seen, so it's better that it's clarified. Okay. So, very good. So, this is not at all an obvious statement, but if you look at the space of parabolic systems, which I'm not defining now, but you can sort of imagine how you define this, those that are self-similar, by that I mean that come from the unstable dynamics of something hyperbolic, they're quite rare. In the cases that I know of and I know how to describe, there are positive codimension submanifold, or union of those. All right. So in view of what we've seen, well, we can, I think, conjecture the following thing, that the generic parabolic dynamical system satisfies the central limit theorem. And as far as I can do numerics, it seems to be the case. Okay. I don't have a formal proof to offer for this conjecture, but it seems to be true. So now I suppose you'd be very vindicated to have following issues that here I've not defined anything. I've not defined the word parabolic. I've not defined the space. I've not defined what it means to be generic. And that's an issue I think that's not that easily addressed because, as I said earlier, you have like a lot of ways you could define parabolic. So I think what's best is to take, concrete examples where there's no debate or where, they're restricted enough that you have some formal statement. So here is just a suggestion. You have many different ways of doing it, probably a theory to build, but this is a very sort of simple, restricted context where you can ask formal questions. So I'm taking one of these three-dimensional maps that I introduced earlier. So here my parameter alpha, for things to work, I need to take it irrational somehow. And what else do I do? Well, I take the map that I considered earlier, that was linear with derivative, that was this unipotent matrix, and I'm adding some smooth perturbation, okay, in one coordinate. But so the reason why I chose this thing, so it only depends on these two variables, x and y, and that's so when you do the computation of the derivative is still unipotent. It just changes and it becomes a bit nonlinear. And the point of that, and that gives us a family of parabolic system on the torus, very restricted, but that's parameterized by a big space, which is the space, okay, there's a typo here, the space of functions of the two torus into R. It's quite big. And so now we've got a space to ask our questions. Okay, so if you want to make it very rigorous, you say for a generic phi, so phi is the function that defines my map. So you think of it as the map. For generic phi, you take an arbitrary observable, and here it's a standard caveat that you have to ask that it's not a coboundary, otherwise there's nothing to be said. So a function is called a coboundary if you can write it as the difference between a function and this, so h, and this function composed by the dynamics. Yes, that's pretty standard caveat. Yeah, sorry, I should have written this in the slide, what a coboundary is. Sorry about that. And so for such functions, the central limit theorem cannot hold true for stupid reasons, so you have to discard them. So you assume it's not of this form. Now you take your Birkhoff sums. I could have taken f to the average 0. Here I'm not doing this. I'm just with subtracting n times the average. So that's essentially a trivial operation that makes f essentially mean 0, and then I normalize square root of n. And so conjecture, this converges in law as to a normal distribution for some variance sigma. And so this seems to be the case. I've done a fair amount of numerics now, and it seems I can't really find counterexamples to it. I just want to emphasize that, that's a very subjective way of formulating this more meta question that I suggested earlier. All right. Now, so we're going to take a bit of time. Well, I've got, it's good, well timed. So, Misha, maybe this will sort of address, answer partially some of your question. Why is it that we see as square roots? So I'm going to emphasize, so I'm going to try and spend like 3-4 minutes on this slide, that the calculation here seems to be specific to T, but there are ways of generalizing it that it doesn't depend so much on formulae. But okay, this you'll have to take my word for it. So when you take the map T and you iterate it many times, what you see is going to be in the y variable, you're going to see y plus k times x. If you iterate, plus some other thing that depends only on alpha, but doesn't alpha and k, but doesn't depend on y and x. Now, if I take an observable that is of the form e to the 2i pi y, this is just for notation. You could have taken a cosine or a sine. That would have made things like just a bit more annoying to write. So you can think real part of this or whatnot. The Birkhoff sum of these things, they're going to look like this. Exponential 2 pi I times y plus kx. Where k is the number of iterations of the number of times I've iterated things, right? It's this k here. Okay. Now the part in y, I can factor it and take it out of the sum. And now the ak, I don't really want to say what they are. They come from, whenever I take x plus alpha, I iterate once more. The alpha is going to add to the second part of the variable, and I'm going to get a number that just depends on k and alpha. And if you do the computation, it's more or less, trust me, k square alpha, this number. And I factor it out. So the function that I get, it looks like a sum of harmonics. I think you'll agree with this. So, and the important point is that these functions, as functions on the manifold, they're orthogonal. So when you compute, for instance, the L2 norm of this, so when you do the computation of this thing, you have an integral of this, all the off-diagonal terms are going to cancel out. So you get the square of the L2 norm, and this is sort of, standard calculation. When you have a square root, it comes from orthogonality. So an analyst told me that once, and that you're stuck with me. And you get an n, so when you normalize, you get square root of n when you take the square root of this. So that's the essential reason why you get a square root. So what I claim is that this general reasoning you can do is far more general. So
But
yes, Michel.
well, so in the usual situation when it is IID, then they are mutual, almost the orthogonal or almost mutual orthogonal to consecutive terms. Here somehow you have this basis is almost invariant. So what is?
So you're absolutely right. So again, I said at the beginning, you'll doubt that this is general enough that it's because I've taken a specific basis. I'll say a word about why you should believe that this generalizes
Yeah.
more general things. I mean, this particular reasoning, then you have a basis, you can decompose any reasonably regular function in this basis, and that will definitely give you this result up to some constant. That is fine. It's Fourier analysis. Now, whether you can apply Fourier analysis to general manifolds and general parabolic maps is debatable, but I'll address that in a minute. So the general idea, maybe if it's not clear at this stage, is that taking functions of this form, which are just simple sums of harmonics with some coefficients of modulus 1, they're a good toy model for Birkhoff sums of parabolic systems. Okay, so I'm going to make this point. So one idea that I'm going to try and insist on is when the coefficients there, they depend on the dynamical system. And when I vary the dynamical system, I'm going to vary the sequence. If I take a big space of dynamical systems, I could hope that these numbers, they become a bit randomly distributed. All right, so now I'm not convincing you of anything. I'm just going to drop a big word. This computation was very linear, Misha. Now, if you use standard tools from what people call microlocal analysis, which essentially allows you to do Fourier analysis on arbitrary manifolds, you can make this bit rigorous and at least run this argument. The price to pay is to learn microlocal analysis, but this much you can do. All right.
Well, I guess my problem is not in the rigor, but just in the intuition, because my intuition was in order to have the square root of n, you need orthogonality, so you need almost independence of the consecutive shifts.
No, but you're absolutely right. You're absolutely right. So what happens if you were to think about it? Here you've got what you get. You start from a function that is y, and when you iterate your map, you're going to get a function here that when you locally linearize, you get the derivative of t applied to y. And because your derivative is parabolic enough, the derivative of the functions that you put in, so to speak, the phase of these functions, they're going to be very different. So now it's a general lemma in analysis that if you take two functions e to the 2 pi I times a function, and you do the scalar product of them, they're going to be almost zero if the derivatives of these functions, they're not the same. It's called the stationary phase lemma in analysis. So
Okay, thanks. So yeah.
Okay, so that's how you sort of do it. Anyway, but thank you for forcing me to justify this. All right, so now again, so this is one of some sort of justification why this could work. So now I'm going to work on this toy model, and I'm just going to say what you would find if you were working with this and you took the AKs chosen at random. All right, so I take my harmonics there. I think of it as my observable, and I'm sort of.
If I just sit on that couch? Sorry.
That's all right. So you take this sum, and I'm going to make the assumption that my Birkhoff sums, they look like that, and the AK are chosen at random. And you can ask, well, for these things, what's the distributions of such things? And so this construction, where I take a sum of harmonics and I put a coefficient in front of them that's chosen at random according to some independent identically random variables, it's called the white noise and probability. And it's a fairly easy theorem from probability theory that if you take such sums, their law converges to a normal distribution, the variance of which you can compute. All right. So what I want to sort of maybe convince you of, or that's the way I think of this problem, is that if this sort of simplification holds true to a degree that can be made rigorous, Birkhoff's sums of parabolic dynamical systems really behave like sum of harmonics there, where you've chosen coefficients in front of your harmonics that are random. Depending on the dynamics, and that those coefficients became random when I vary the dynamics, appealing to this general theory of white noise, then you should have a central limit theorem. Now, so the first bit I think is reasonable to believe that can be done with tools available. For the second one, I've not thought very deeply about it, but it doesn't seem easy. And so that's more of an invitation to think about these questions. There you go. Thank you.
Okay, let's thank Salim. Questions?
So what would be the simplest example where you don't have the square root of n?
So you've got a handful of examples where you don't have the square root. So you have rotations.
So what happens in this example?
Very good. So for rotations, provided your rotation number is not too bad, let's say the golden ratio, or if people are familiar with the terminology, with the rotation number is Diophantine, then the Birkhoff sums of a zero observables are bounded.
Yeah.
And that's very easily proven using Fourier analysis. I mean, very easily. It's an exercise.
Kind of some more interesting examples when there is some polynomial growth, but different from one half.
And so now you have, the only examples I think that I know of, and I suspect in the world of smooth dynamics, there will not be any others unless you do, I don't know, are interval exchange maps. Or flows on translation surfaces where you can have pretty much any growth rate, which again comes from the fact that they're renormalizable by a dynamics that is that has some special Lyapunov exponents that will drive the growth of these sums.
So we should not think of interval exchange maps as some kind of parabolic dynamical systems. It is a different type.
So it depends. So if you think of it as a geometric thing, locally, you compute the derivative. The derivative is 1. It's a translation. There is no mechanism for shearing or for growth of the derivatives when you apply. So when you look at if you look at the mechanism in this proof here that generates the orthogonality, it's not there in the theory of interval exchange transformation. So
it is closer to elliptic case. So
yes, it's closer to elliptic case, and I mean it shows in many different ways when you unfold the theory.
Okay.
I could say more about this, but yeah, that's just.
Okay. Can I ask a question about not so much about the math, but about the numerics?
Yes.
So when you're doing the numerical simulations, are you using finite precision?
Yes, I'm using. I mean, I don't know what you mean by finite precision, but yes, I am. Of course.
Oh, yeah, finite meaning that this is not an infinite precision, arbitrary precision computation.
No.
Yeah, so there is just a comment. So there is some interesting older literature about what you get when you discretize hyperbolic dynamics in this way.
That's
That I'm sure you're aware of,
I know where you're
and
getting.
yeah, and they're interesting phenomena that combine, which are also ergodic in nature, but they have to do with the effect of discretization
Yeah,
of the dynamics. So I'm not actually aware that I don't know that anyone has done this on with parabolic dynamics. With non-hyperbolic dynamics. So just as a general remark, that there could be a mix of phenomena here. So
Okay.
what you're observing.
So can I make a comment, because this is
Of course.
a great question, and I'm glad that I have someone who at least appreciates. So you cannot do numerics with hyperbolic dynamical systems, at least not with a normal computer, because of the exponential sensitivity on initial conditions. The growth on the error that you make by discretizing grows exponentially fast, and exponential of 10 is already enormous and beats the precision of your machine. So if you take 10 iterations of a hyperbolic dynamical system, what you see after 10 iterations can be extremely far of what you wanted to measure. Whereas in parabolic dynamical systems, because the growth of the error is polynomial, you can rigorously at least do things, and that's what I observe is definitely the approximation of a Birkhoff sums, of a Birkhoff sum. And somehow when you do numerics on hyperbolic dynamical systems, you see probability theory, but for reasons that have absolutely nothing to do with dynamics. Yes.
Kind of always thought that in hyperbolic dynamics, the shadowing phenomenon can save the day for computations.
So there is some, all of this is debatable, I think. There is some literature on hyperbolic. My comment was just that there are some effects of discretization in all of this present. So but I don't know what impact they have. I get your point on the growth of error, that there is
the only point I wanted to make is that for parabolic things, so for all these things, I've checked that the precision of my machine was good enough that it, would not fail me, and I would see what I can see, because I've also tried to do hyperbolic, and sometimes things go wrong. I've asked people who are sort of specialists of this, where you've got Pierre-Antoine Guilleneuf from Paris. He's done his PhD thesis on these kind of questions. And he told me they've got a lot of complicated questions. Now, I don't know the whole literature, but he told me, parabolic is fine. So, yeah.
Okay, let's thank you. Let's thank Salim again. And we have 3 minutes.
Give us a little bit more.
4 minutes.
6. A cup of coffee.
Well, let's say 5.
Misha, are you host? Because I need to share.
I just gave you co-host
Oh,
privileges.
okay, thank you. All right. Well, I'm gonna turn off. You don't have to watch me do this. So, sorry. Michael, you have to give me it. You actually have to give my iPad permission to share.
Which is your iPad? What?
Well, which is my iPad? Here, I'll show my. I'll show my picture on this iPad. So now you can see.
Okay.
Now I'm gonna hide that picture.
So is this all right now?
I think it's fine.
Okay.
I'm doing my share. Okay. So there's that. Okay. Now I'm going to the meeting.
Very good.
Again, would you like to be in charge?
Sure. Okay, it's my great honor to introduce Professor Amy Wilkinson from University of Chicago to give the last talk today. She's going to talk about stable ergodicity of symplectomorphisms. Please.
All right. Thank you so much. Thank you for the invitation. Let's see what time it is. All right. Yes, after Salim's beautifully like spare, minimal, non-technical talk, I'm going to slam you with a technical talk. So apologies in advance. Since I usually cannot follow talks that are slide talks over Zoom, I'm doing some kind of hybrid situation here. So I've written part of the talk, but I will write the rest of the talk as I give it. So today I'd like to talk, hopefully get to some kind of moderately recent work with Arthur Avila and Sylvain Corvisier, and some of it with Julien Zhang. But I might not get to that point. So I'd like to give you some background and motivation first. The setting for this talk is completely symplectic. I will mention occasionally volume-preserving diffeomorphisms, but for most of this talk, M is a symplectic manifold with a symplectic two-form omega, which is closed and non-degenerate. And I will denote by diff R subscript omega of M the set of CR diffeomorphisms that preserve this form. So they're also called symplectomorphisms, although that's a little challenging to pronounce. And throughout, I will denote by M the volume on the manifold, the probability volume that's induced by this form. And any symplectomorphism will preserve this volume. And so we can do kind of ergodicity, do the ergodic theory of symplectomorphisms. There's always a very natural invariant measure at hand. Now, the real subject of this talk, or the star of this talk, is a special subclass of symplectomorphisms, or in fact, a special subclass of diffeomorphisms, which are the diffeomorphisms that are partially hyperbolic. So I will use this notation. So this is just the space of CR diffeomorphisms of M, partially hyperbolic. And I'll say a minute, at least informally, what that means. But I will often decorate term with an omega. And if I do, I'm talking about the symplectomorphisms. And sometimes I will decorate it with vol. And by that, I mean the space preserving a volume, a fixed volume, absolutely continuous, or some volume absolutely continuous, or equivalent, I should say, to a volume measure. Okay. So now, what do I mean by partially hyperbolic? Well, if I have such a diffeomorphism, partially hyperbolic, sometimes, by the way, I'm going to drop the M in question if I'm just talking about a general symplectic manifold or a general manifold. So, I might not write that. But if I have a partially hyperbolic diffeomorphism, if at minimum, it must be C1, and I want to denote by EU plus EC plus ES. It's partially hyperbolic splitting. Now, what do I mean by this? I mean that the vectors with respect to some Riemannian metric on M, the vectors in EU are uniformly expanded by the derivative of F, and that bundle is preserved. And similarly in ES, vectors are uniformly contracted, and that bundle is preserved. And then in the central bundle, you see domination. Domination from the other two bundles, not expansion, but not as strong as in EU, and contraction, but not as strong as in ES. And I want to denote this, use that notation finest partially hyperbolic splitting. Because F can be partially hyperbolic, but not, the splitting might not be unique. It might be partially hyperbolic in more than one way. So I want, in particular, I want EC, maybe I don't mean finest, I mean minimal. Sorry, that's more. Okay, so minimal with respect to EC. So EC cannot be, parts of EC cannot be further split off to become unstable and stable bundles. So the general theory, I'm actually going to assume knowledge of partial hyperbolicity for this talk. So I apologize if you were looking for a little more gentle an introduction, but I will give some examples. In any case, this bundle EU is always, from general theory, tangent to a foliation WU, which is like the unstable foliation in the Anosov case. The Anosov case, by the way, being when this bundle EC is trivial. Okay, and similarly, there is a foliation tangent to ES called the stable foliation. And the dynamics of these foliations play an important role in the properties of F itself. So the question, as announced in this talk, that I want to address is really which, not who, but which F symplectomorphisms, let's start with symplectomorphisms, which are ergodic with respect to M, to be clear. So the basic property of ergodicity, meaning that there are no invariant sets of intermediate measure. So ergodicity of smooth systems is, of course, something that's been studied for a very long time. And it's known, for example, that on any symplectic manifold, you can produce diffeomorphisms that are not only not ergodic, but if you perturb them in a high enough smooth topology, they will remain non-ergodic. So the general answer to this question, for starters, is not all. Here's an example of a partially hyperbolic system. I will return to this question on the 4 torus. So I'm going to take a product. Now, literally, thank you so much, Salim, for introducing things like the cat map. So I can be kind of quick about this. So I want to take a product of just two maps. The first is 2111, the cat map squared, linear map on the first factor. And on the second factor, take a map from the standard family. So there's a parameter lambda. And one can check that this is partially hyperbolic if lambda has modulus less than 4. So that's like an exercise. It also preserves a symplectic form, the symplectic form just being the sum of the area form or symplectic area form on the first torus plus the area form on the second factor. Yes, apologies to Michael Yampolsky. This picture of an orbit of a point under A is, of course, highly inaccurate. It's probably not actually the orbit of a point in A, but it gives you a sense, a point under A, but it gives you a sense of what the dynamics are like in the first factor. They preserve area and they're very highly chaotic because the first factor is an Anosov diffeomorphism. The second factor, here I chose the parameter value of 3 lambda is 3/4, is sort of evidently not ergodic. It has a fixed point that's elliptic, It is a resonant fixed point, so you can't directly apply KAM theory to this, but I think maybe you can apply some Mather theory because there is some twist. In any case, just looking at it, it seems pretty clearly not ergodic because there are these invariant circles. The sort of KAM phenomenon is that there would be a positive measure set of invariant circles corresponding to ellipse or circles or ellipsoids on which the dynamics, because these are invariant, are Diophantine irrational rotations. So we'll return to this type of example. But here is a picture of the product of the two maps. It's a product. There's no interaction between these two maps, but it is partially hyperbolic. The hyperbolicity coming from the Anosov factor, so the EU and the ES sort of being horizontally situated, and then the EC is tangent to the vertical fibers of this map. And this product is, assuming you agree with me that this is definitely an invariant circle, is evidently not ergodic, because if I take the product of one of this invariant circle with the other torus, I get a codimension 1 invariant torus that separates the dynamics. It's an obstruction to ergodicity. But anyway, this is a good test example for our future questions. Please stop me if you have any questions. So I just want to give a little background about the ergodicity of symplectomorphisms. The first result is, and I just want to remark, which topology is chosen is going to make a big difference in kind of what the answer is going to be. So I mentioned earlier, I probably should have written this down, but there's this KAM phenomenon that says if you have an elliptic fixed point with enough twist, you're not going to be ergodic because you're going to have this family of invariant tori, codimension n tori, that block ergodicity, so they're a positive measure. But okay, that's sort of the first kind of classical result. If you back off of ergodic theory a little bit and ask a question that's very similar, so what's a similar question? So if I have an ergodic diffeomorphism preserving a volume, almost every point will have a dense orbit. Okay. And that's just a consequence of ergodicity. So you could ask this question, the existence of a point with a dense orbit, that's called topological transitivity. And Arnaud Bonnetti-Crovizier proved some time ago that the property of topological transitivity is generic. Is C1 generic in the space of C1 symplectomorphisms of our symplectic manifold. So in some very crude sense, properties that are kind of implied by or very similar to ergodicity are already known to be kind of generic, but in the C1 topology. I wanted to mention next an interesting kind of circle of results that are going to kind of focus us in onto this class of partially hyperbolic systems. And so Rita Tazibi and Sagin Shah proved there that if I have a symplectomorphism, any regularity, and I know it's stably ergodic, so maybe I should put a C1 here. C1 stably ergodic. Then F is actually partially hyperbolic. Ergodic. Okay, so what do I mean by stably ergodic or C1 stably ergodic? Well, inside the space of C1 symplectomorphisms, I could look at the ergodic isms. Stably ergodic, if not as ergodic, morphism is ergodic. And what these guys showed is that if you are stably if you are not partially hyperbolic, then you can find after C1 perturbation an invariant disk for the dynamics. You can do this in a symplectic way, and that violates ergodicity. Right. So I said before, moving on to the next kind of background result, these are like from the 2000s, late 1900s. Wait, really? Late 1900s, early 2000s.
If you consider the generic perturbations, can it be non-partially hyperbolic? So if you consider, so you want ergodicity only for generic perturbations, would it make the difference?
Well, let me just, so one remark I didn't make is inside of diff omega is a possibly empty but open set of partially hyperbolic symplectomorphisms.
Yes.
So this is an open property itself. Okay.
Yeah, but if you consider kind of, you want some diffeomorphism which is not partially hyperbolic, but generic perturbations are ergodic. Can it exist?
So you want to, instead of saying stably ergodic, you want to say the generic perturbation is ergodic. That's very similar to stably ergodic. But let's see. Off the top of my head, I don't know the answer to that, but I will have other similarly generic things that I'll mention.
It's not known for.
Yeah, I don't think it's known. Yes, thank you, Sylvain. I'm glad you're here. Okay, but it's a good question. So I mentioned ergodicity, that almost every orbit is dense. So what about this property of almost every orbit being dense? It's also implied. So we call this property metric transitivity. And as a consequence of a theorem proved by Dolgopiat and myself, so i.e. almost every orbit dense, this property holds C1 open densely in the space of pH1 omega of M. So why is this the case? So this is also true in pH1. I could also put a vol there. Okay, but we did prove this in the symplectic setting. So what's the mechanism behind this result? It's a property of partially hyperbolic systems called accessibility. And what we prove is that accessibility holds or contains, I shouldn't say isn't necessarily, but it contains a C1 open dense subset of the partially hyperbolic symplectomorphisms. What is accessibility? Well, recall that we have foliations tangent to ES and EU, the stable and unstable foliations. And accessibility says that given any 2 points P and Q in my manifold, I can get from P to Q along a path such that each piecewise C1 path, say, such that each segment is tangent to either the stable or the unstable foliation. Okay, so there's a property that automatically holds for Nausseff diffeomorphisms, because in that case, EU and ES are transverse. But more generally, that's not an immediate consequence of partial hyperbolicity. So we prove that accessibility, this property, is actually open and dense. And then there's an argument of Misha Brin from the 70s that shows that for a conservative system that's accessible, almost every orbit is dense. So that gives the transitivity, metric transitivity. Okay, so this is background of like what is known. There is another result I'm going to mention, a few more results I'm going to mention. But before I continue, now that we've sort of focused some attention on the partially hyperbolic systems, I just want to mention a conjecture of Pugh and Shube from the mid-90s. So what they conjectured is that if we consider the volume preserving CR diffeomorphisms of any manifold, I should say vol, the property of stable ergodicity what they meant by stable ergodicity was sort of C1 stable ergodicity. So any C1 small perturbation is ergodic. That this and same C1 stable accessibility that I just defined. So imagine that property, but preserved under perturbations. These are both CR dense. And so in their context, they imagined R actually being greater than 1, but the stability being a sort of a C1 open version of stable ergodicity. One could ask the same question for other types of openness and other types of density. And these are interesting and largely, unsolved in this context. So we can, yes.
This suggests that this should be true in the real analysis. It is.
They suggested what?
That the conjecture should be true also in the real analytic case. So
I haven't, the real analytic partially hyperbolic systems like real analytic and Nausseff systems are pretty rigid. So I don't know exactly what the correct analytic formulation is, but I don't know if they thought about it. But it's again a good question to explore. So Dima Dolgopiat and I proved the case of stable ergodicity or stable accessibility being C1 open and dense. So sort of in the case R equals 1, which and there's some other results known for CR density when you assume that the dimension of the center is 1. So that's by Federico and Hannah Rodriguez Hertz and Raul Uris. So it was actually for stable accessibility. The dimension EC is 1, R equals 1. So of course, dimension EC equals 1 is precisely, well, I should say, of course, but dimension EC equals 1 is precisely not the case of symplectomorphisms. The reason being that the structure of the derivative of a symplectomorphism gives a symmetry in the spectrum. And so any center bundle, as a general rule, if your center bundle is minimal and is not 0 dimension, it has to be at least 2-dimensional. Right? So pretty open in the symplectic. So one could ask this, well, it's just a motivating question. You could also ask this among the symplectomorphisms. I think there's a good chance it's probably true, but it's pretty open. Here is what is known, though. So Keith Burns and I proved a criterion for ergodicity of partially hyperbolic systems. So we proved that if a volume-preserving partially hyperbolic system is center bunched and accessible, then it's ergodic. So I will say something more about this criterion in a little bit, but if you combine that with what Dolgopiat and I did, you get this conclusion. And so I want to highlight this conclusion because it's fairly definitive in sort of the C1 topology on C2 symplectomorphisms. So there's this extra condition called center bunching that is needed in this setting. And just draw a sort of a heuristic picture of center bunching. Center bunching is a condition on the expansion and contraction rates in the stable center and unstable bundles. It's an open subset. The systems that are center bunched form an open subset of the partially hyperbolic systems. So it applies to many examples, this criterion. So let me give you an example where it does, it's the same example as before. Let's consider product of this Anosov with the standard map. As I said, it's partially hyperbolic for lambda between -4 and 4. It's actually center bunched for a nice reasonable size set of parameters. So if I take lambda and -1, 1, in fact, this is if and only if, so I should say, you can find a periodic obstruction to center bunching when lambda is 1. But it is center bunched when lambda is between -1 and 1. And in this example, Shub and I a while ago showed that this example, in fact, any partially hyperbolic example of this form can be smoothly perturbed symplectically C infinity if you want, of T4 to obtain an F that is stably accessible. And then in this case, the theorem with Keith, or even by earlier work of Pugh and Shub, so really there's an earlier version of our theorem, this implies that you can fairly close to this example with this codimension 1 invariant torus, you can get a stably ergodic example. This is if lambda has modulus less than 1 and the center bunching holds. Okay. And so the idea being that previously the stable and the unstable foliations were jointly integrable And so you could not have accessibility because you could not get off a horizontal torus using these foliations. But without too much work, you can symplectically perturb F so that the foliations are no longer jointly integrable. And along with center bunching, that's enough for stable ergodicity. Okay. Yes, Misha?
No, just
Okay.
just listening.
Okay. So that's the idea. It's kind of cool. That settled a bet with Steve Smale, actually, that paper where we did the accessibility. Anyway, so Artur and Sylvain and I, a few years ago, managed in the space of C, inside of the space of C2 partially hyperbolic diffeomorphisms, we were able to show that stable ergodicity is C1 open and dense. So we showed C1 density, but this is in the case of volume preserving diffeomorphisms. So it's a completely different argument. It does use accessibility, however, in a different way. It uses metric transitivity. But the key starting point for this argument is that the generic diffeomorphism, partially hyperbolic diffeomorphism, is C1 generic is non-uniformly hyperbolic in the volume preserving setting. That is not true in the partially hyperbolic setting. In the partially hyperbolic setting, you can have stable examples. For example, the example I just gave you with an elliptic periodic point. So you cannot have hyperbolicity in that. In fact, I mean, even you can't have hyperbolicity along any of these invariant tori, but in particular, you can't have a splitting when you have an elliptic periodic point that's any finer than one with a two-dimensional center. Okay, so it's definitely, the argument just doesn't work in any way, not in the symplectic setting. Okay. So what this talk is about is how can we maybe try to get stable ergodicity in the symplectic setting where we can't use non-uniform hyperbolicity. We cannot assume that. Okay. So are there any questions at this point? Okay. Oops, the chat's not open, so I can't see if there's any chat questions. Nope, I don't see any. Okay. Let me make the screen bigger. So I can see, not see all your faces, but at least see your names. All right, so this brings us to a result. This is from, again, a lot of this work, not as many people work on these problems these days, but there's so many interesting problems still there in the study of partially hyperbolic systems. But this brings me to a work from 2009 with Artur and Jairo Bocchi, where I will explain below, but we proved that ergodicity is a generic property inside of the C1 partially hyperbolic diffeomorphisms, symplectomorphisms on any manifold. So again, this is a C1 genericity result. This generic set probably doesn't contain any C2 diffeomorphisms at all. So let alone C infinity. So it's an interesting, it's an interesting result, and the argument I think is really lovely, but it doesn't give stable ergodicity. We'll go into why it doesn't, but it does give further evidence that for partially hyperbolic symplectomorphisms, ergodicity is something that one might expect to be a general kind of property. Okay, so I'll explain this argument below. I'm also going to explain the argument with Keith Burns. And then maybe say a few words about how one might generalize this. That's the more recent work. So we still have this open question, and we can add to that Misha's question, but is stable ergodicity dense in any sort of sense? Stable in any sense, dense in any sense, in any class you want of partially hyperbolics outside the center bunch setting. So in our example, just to kind of make concrete the open question I'm talking about, if we look at our example, the question is, take lambda between 1 and 4. Can you approximate this in any sense by a stably ergodic map? You can actually smoothly approximate it by something that is accessible, stably accessible. That's what Mike Shub and I did. But stably ergodic, I don't know. I still don't know the answer to this question. But here's an example where you take lambda outside of this range and you get this kind of funny face portrait. Okay. So I want to tell you about center bunching. Let me just say in words what center bunching is. Okay, so remember, bundle to M for any partially hyperbolic diffeomorphism has a splitting into these 3 bundles. And the derivative of F preserves all 3 of these. Now, center bunching, which appears in many other contexts, sometimes fiber bunching, you see, is a similar concept. The center bundle, the dynamics can be quite kind of wild in these directions. And you can see expansion and contraction. You can measure the kind of how conformal, so some kind of measure of non-conformality of the derivative in this center bundle. So if the derivative were the identity, the non-conformality would be 1. Otherwise, the non-conformality of the derivative is measured by a ratio like this. This is a number less than 1. This is the least expansion of the derivative under, in this bundle under the derivative of F, and this is the greatest expansion here in the denominator. This is a ratio of less than 1. Center bunching says that that ratio at every single point has got to be not small. It can't be as small as the weakest action in the stable bundle. So the non-conformality is dominated by the hyperbolicity. So non-conformality in EC is sort of dominated in some sense by the hyperbolicity. And you can measure at a given point, you can measure these 2 non-conformalities both in forward and backwards time. That I'm using, the way of measuring lengths, is kind of, I have freedom to pick it. So if I can find some metric where this is true for every point, I say it's center bunched. So this is clearly like a C1 open property. And if the derivative is the identity in the center, then you have center bunching. So for example, that's how you figure out the range of center bunching for this family, because when lambda is 0, the map in the correct norm, you can make this constant as close as you want to 1. Okay. And so this center bunching condition, and I broke it into uniform and uniform center forward bunching and uniform center backward bunching. Keith Burns and I showed is that if F has this center bunching, it's C2, which is sort of a standard smooth ergodic theory assumption, then for any measurable set, if it's invariant, then if I look at the Lebesgue, so this denotes the Lebesgue density points. So, oh, and this, sorry, this should be volume preserving. I left that out. The set of Lebesgue density points of A has an interesting property of being saturated by both foliations, the unstable and the stable. So what does that say? It says if I have an invariant set, so let's assume it has a positive measure, okay, so that the set of density points is non-empty. Well, Hopf's ergodic theorem applies invariant set altered on a set of measure 0 so that it is saturated by leaves of the stable foliation, or let's say unstable to keep my colors. Okay, whatever. Leaves of the unstable. And again, a Hopf argument using the ergodic theorem says that this set, after changing it on a set of measure 0, is saturated in the stable direction. What this theorem says is under the center bunching hypothesis, I can select a full measure subset, a canonical full measure subset of my set A, namely the Lebesgue density points, and that set, anywhere I go in that set, it's fully saturated. Every point on the stable and unstable manifold through that set is a density point for my invariant set. So in particular, so that's a sort of a technical statement of what we proved, but in particular, what this means is if I have a volume preserving, I could, for example, a symplectic partially hyperbolic diffeomorphism. So is center bunched, has the accessibility property, F is ergodic. For the simple reason that if I take an invariant set with positive measure, I can replace it by a set of the same measure contained or up to a 0 set of density points. And then every single density point along stable and unstable manifolds remains a density point. And so starting with a density point and any other point in the manifold, I arrive along stable and unstable manifolds to a density point, another density point for A. So the whole manifold is a density point for A. So A is full measure, QED. So that's the argument. And it uses things called Juliennes that were first invented by Grayson, Pugh, and Shube. It's a rather involved argument that I'm not going to go into, but this is the kind of core result.
Maybe you can give some hint why the conformality helps to do this kind of arguments, to do the Hopf argument, why conformality, so what it It is for
Well,
some distortion estimates, or what is the role of
well,
the
it
zeta
literally
bar?
would take me about 10 minutes to give a good explanation for why this is true. But it's very useful in several ways. One is that center bunching essentially implies that if I have a curve that's tangent to the center direction, the unstable manifolds will vary in a C1 way through that curve, and so will the stable manifolds.
I
And
see.
so it allows you to control a certain kind of distortion under holonomy. It's called Julienne. You start with Lebesgue density points and you move to something called Julienne density points, essentially. And then using center bunching, you show that Julienne density points are invariant under holonomy. And so this gives you that density points are also invariant, Lebesgue density points for
Okay.
invariant sets. But
Thanks.
that's sort of
Thank you. Yeah. Yes.
well, I will try to give some mathematical content, although I'm not. Yeah, I recommend reading that paper. It's really not a bad paper. With Burns. Okay. So now I'm describing the work with Avila and Boki. And I'm probably have 5 more minutes. So I'm going to maybe go a little bit faster. These are the definitions from before of forward bunching and backward bunching of a point, P. And what this is from my paper with Artur and Jairo. This is our definition, sort of a pointwise version of center bunching. Kind of an asymptotic version of forward and backward bunching. In fact, definition of center bunching, I could replace these two properties that I just defined by these two properties, which are asymptotic properties. And if these two properties hold for every point, then you have center bunching. So this is kind of a refinement, a more metric dependent, independent refinement of the property of center bunching. That you can say a point is center bunch. But of course, this is a non-uniform definition. So it allows for different so bunching kind of, or different, you can quantify the bunching by a parameter that can change from point to point. So this is a new definition. I'm not going to go through why we defined it this way, but there's just some important properties about this definition can be described in a simpler terms in terms of Lyapunov exponents when you have them. So I'm just going to denote the set of points where you have center bunching forward or backwards by CB plus and minus, and CB, which is really CB of F, but I'll usually just say CB. That's just going to be the intersection CB plus intersect CB minus. So these are the bunch points. And there's some facts. The set of forward center bunch points is saturated by the stable. This is not hard to see. And the backward center bunch points are saturated by the unstable foliation. And this is kind of what I'm going to use in my last few slides. If you take any invariant measure for M, and you look at its Lyapunov exponents, say ergodic, but it doesn't matter. Look at its Lyapunov exponents in the center. Have this of inequality holding at the point P. It's a relationship between the expansion, the the stable direction, yeah, maybe actually, I think I probably need actually something a little bit stronger on the left-hand side. Maybe you need to take some kind of supremum. But basically, if a property like this holds, then P is forward center bunched. So the takeaway is just something like the following. If all center exponents, EC exponents for mu are close to zero, where the closeness is determined by the expansion and contraction in the stable and the unstable, then you conclude that almost every is center bunched. Okay, so this is the key thing I'm going to use. And I wanted to state and prove, give an idea of a proof of our theorem parallel to the theorem with Keith Burns. We don't assume center bunching. We do assume, however, volume preserving. If you have an invariant set, the density points might not be saturated, WS saturated, but if you intersect them with this WS saturated set, CP plus, then your set is WS saturated. And similarly for CB minus. So it's just a non-uniform version that allows you to isolate the center bunched parts of your manifold. So I'm going to show you how this argument goes. So it's via a Baire argument, of course. What it boils down to showing is the following. And this is like an almost ergodicity statement. So if we have any epsilon, C1 densely, and in fact openly by some argument, set of diffeomorphisms have the property that any invariant set either has measure zero or measure less than epsilon or co-measure less than epsilon. And here are some of the ingredients in the proof. So we use in a key way an earlier argument of Bocchi in the symplectic setting that if F is not a Nossoff, then the center exponents in the finest or minimal partially hyperbolic splitting are all zero almost everywhere with respect to the canonical measure. Then there's a kind of continuity of Lyapunov exponents property that when you combine it with Bocchi's argument, says that in an P1 open neighborhood, one of these diffeomorphisms where you have all the exponents zero, you still have really small exponents on a large measure set. So the measure of the center bunch points is still quite large. And then the non-uniform Burns-Wilkinson that I mentioned before. And the final thing we use is, I can summarize this. Basically, if I'm in a situation where F is not a Nossoff and my center can't be further broken by Bocchi's arguments, then in the center direction, you can find an actual, after perturbation, a periodic disk that's tangent to EC. Initially, this is using like an ergodic closing lemma type of argument. Initially, the disk maybe the derivative is just elliptic, but you can make it periodic, truly periodic. And you can do it in such a way where the dynamics on this disk is center bunched, or the orbit of this disk. So the orbit of the disk actually belongs to the center bunched set. And secondly, the derivative or the return map on this disk is ergodic. And that's what you do is you take that periodic disk, you symplectically paste in an Anosov-Katok example, symplectic. Okay, so this is my picture of the disk. And now let me prove for you almost ergodicity. And then I really have to stop. Let's fix an epsilon greater than 0. And pick an F. So there's a dense set of these. So with these two properties, so this is dense, next two properties are dense. I want an Anosov-Katok disk as above, and of the center bunched points for F is greater than 1 minus epsilon. Okay. And then here's a picture of the proof. We'll just end on this picture. So here I've drawn the Anosov-Katok disk right here as just a line segment because I don't have enough dimensions. So that's tangent to the center direction if you look in this little thing on the side. And I can take the stable manifold of this disk, and because the center disk is center bunched, right? This is contained in CB, its stable manifold is forward center bunched, right? Because center bunched is CB plus is stable, saturated. So now suppose I have my set A, it's invariant. Suppose its measure is bigger than epsilon. On the other hand, over here, I have my center bunch set, and I don't know, maybe I should have, just to be safe, it has really high measure. Okay. So the intersection of these two sets has positive measure. So here's a set that's contained in the intersection with positive measure. Accessibility, or more specifically metric transitivity, says that almost every orbit is dense. Assuming accessibility, but I forgot to say this, accessible. That's an open dense property, so I'm going to assume it. So I can assume that set E, after iterating, because still belong to this invariant set, is very close to the stable manifold of my disk. And particular, it's contained in CB. If I look at its unstable manifold, it has to be, because unstable manifolds are WU saturated, and this set is WU saturated. Its unstable manifold belongs to density points of A and are also backwards center bunched. Yes.
Somehow I just lost your pictures. Is it my problem or just general problem? So,
Oh, the picture's gone?
at least on my screen. So other people have them.
No,
Did you lose one?
it's gone.
Wait, it's gone or no?
Yeah, the video should be fine.
It's fine. Okay, so it's a problem with
This is my problem. Okay.
with Misha. Okay. So I've taken the unstable manifold of this set E and I intersect it with the stable manifold of my center bunch disk. So points in this intersection are both backwards and forward center bunched. So here I am actually applying this theorem, the earlier criterion for ergodicity. So now I look at the intersection. I have a set F. It's still a set of density points. Its points are center bunched, and they now lie in this disk. And because of absolute continuity of the unstable foliation, it has positive measure in this stable manifold of the disk. My final step is to apply the theorem again. I can saturate F now because it's center bunched. It's beautiful, right? I can saturate again, and all those stable manifolds are also density points. And so when I intersect them with the disk, I get a new set G that has positive measure and consists of density points. But now the set of density points and the set of center bunch points are both invariant. So I can iterate many times, and using the ergodicity, the Anosov-Katok ergodicity, I get that the measure of this set, the density in this disk, is 1. Well, similarly, if the complement also had measure greater than epsilon, then I could show that the density points of the complement had full measure in this disk. Contradiction. And so this is how we obtain almost ergodicity. And I am way over time, so I'm not going to actually tell you about the latest stuff. Thank you.
Thank you, Amy, for the great talk. Any more questions?
Oh, it looks very surprising to me that you can construct this periodic disk in the central direction. So it is kind of, in general, I kind of always.
It's a very C1.
It is what? What is in?
It's extremely C1.
C1.
So I have like 0 exponents. I start out with 0 exponents almost everywhere.
But it is.
I have a lot of recurrence.
Yeah.
And I have an ergodic closing lemma proved by Arnaud in the symplectic setting.
Yeah, but still, a kind of the center manifolds are always problematic. Yeah, so somehow to construct actually something invariant seems to be should be delicate, I guess, or it is not.
You know, in this C1 topology, it's a lot less delicate than you think, because you always sort of have this fact that I think I see what you're getting at. Because for general partially hyperbolic systems, how do you construct a center manifold? There is no kind of canonical way to do it. But once it's attached to a periodic point, you have a better thing. But it's yeah.
But yeah. But you also perturb, yeah, so you allow perturbation of the map somehow too.
Oh yeah, these are all dense. If you go back, these properties are these are all C1 dense properties inside of C2. I mean, they're also C1 dense and C1, but we pick something smooth so we can use something C2, so we can use the ergodicity criterion.
Thank you.
More questions?
Michael, did you have a question?
No.
Oh, because you just turned on your microphone. Anyway.
Oh, sorry.
Okay. Thank you very
Okay.
much.
All right.
Let's thank Amy again and all the speakers today.
Enjoyed.